Imagine building powerful websites, analyzing massive datasets, or even creating intelligent robots. This is all possible with Python. Welcome to the exciting world of Python. In this video, we'll cover what Python is, why it's so popular, and how to get it installed on your computer. Let's dive in. So, what exactly is Python? Simply put, it's a high-level, interpreted, general-purpose programming language. High-level means it's designed to be easy for humans to read and write. Interpreted means the code is executed line by line without needing to be compiled first. And general purpose means it can be used for a wide variety of tasks. Python's popularity stems from its readability, large community, extensive libraries, and versatility. See how easy that is to understand? Python's syntax is very close to plain English, and with its massive community, you'll find countless resources and support. Plus, Python boasts a vast collection of libraries and frameworks. This makes it perfect for web development, data analysis, machine learning, and much more. All right, let's get Python installed. First, open your web browser and go to python.org. Click on the Downloads tab and select the latest version for your operating system. Once downloaded, run the installer. On Windows, make sure to check the Add Python to Path box. This is crucial. After installation, open your terminal or command prompt and type python-version or python3-version. If you see the version number, congratulations, Python is installed. Now let's install a text editor or IDE. I recommend VS Code or PyCharm, but even a simple text editor will do. Next, we will install a Python package using pip. Open your terminal and type pip install Colorama. If you encounter any path issues, you might need to manually add the Python installation directory to your system's path environment variable. Look up operating system specific instructions on how to do that. If you have multiple Python versions installed, you might see version conflicts. Make sure you know which version you are using and that your path variable points to the correct one. To help solidify your understanding and reinforce the concepts covered in each lesson, we've compiled valuable resources that are consistently available. These resources are designed to enhance your learning experience and ensure you grasp the core material. Specifically, you'll find coding challenges exercises. These practical exercises provide an opportunity to apply your newly acquired skills and test your comprehension. Quiz questions. These quizzes assess your understanding of key concepts and help identify areas for further review. Key takeaways. This concise summary highlights the essential points of each lesson, serving as a helpful reference. Downloadable resources. Where applicable, you will find downloadable files such as code samples, templates, worksheets, and other supplementary materials that you can use for offline study and practice. These resources are consistently linked within each lesson's description or accompanying materials. We strongly encourage you to utilize them to maximize your learning and solidify your understanding. If you have any questions, feel free to leave them in the comments below. And don't forget to subscribe for more Python tutorials. Okay, what next? Where do I actually write my Python code? And how do I make the computer run it? Do you type commands somewhere special? Do you need to save them in a file first? These are super common questions when you're starting out. Don't worry, it's simpler than you think. In this video, we're going to learn the two main ways to run Python code. First, we'll look at the interactive mode, which is great for quick tests and trying things out. Second, we'll learn about script mode, where you save your code in files to build bigger, reusable programs. Understanding this difference is super important before you can really start building things in Python. Oh, and before we dive in, remember to check the video description below. For every lesson, I'll include links to related resources like the code snippets we use, challenge exercises, downloadable guides, a quick quiz to test your knowledge, and key takeaways. Everything you need to succeed. All right, let's get started with a little bit of theory. How does Python code actually run? Your Python code, the instructions you write, can't run all by itself. It needs a special program called the Python interpreter. Think of the interpreter as a translator. It reads your Python code line by line, understands what you want to do, and tells the computer how to do it, producing the output or actions you asked for. So the first way to talk to this interpreter is called interactive mode. This is like having a direct conversation with Python. You type one command, and Python runs it immediately, showing you the result. This is often called the REPL, which stands for read, eval, print, loop. Read, Python reads the command you just typed. Eval, it figures out or evaluates what that command means. Print, it prints the result back to your screen. Loop, then it waits for your next command, looping back to the read step. How do you get into this mode? Usually, you just open your computer's terminal or command prompt and type the command Python, or sometimes Python 3 depending on your setup, and hit enter. You'll know you're in interactive mode when you see these three angle brackets. That's the Python prompt, waiting for your command. Interactive mode is fantastic for doing quick calculations, testing a small bit of code to see if it works, trying out new Python features you just learned about, or just generally exploring. The key thing is whatever you type here isn't saved anywhere permanently. Now, what if you want to write a longer program, something you can save and run again later? That's where script mode comes in. In script mode, you write your Python instructions in a plain text file. You can use any text editor, even simple ones like Notepad or TextEdit, or more advanced code editors like VS Code or PyCharm. The important part is that you usually save these files with a .py extension. That py tells everyone, hey, this is a Python script. Once you have your script file saved, you go back to your terminal or command prompt. But instead of just typing Python, you type Python followed by the name of your script file, like Python my program, py. The interpreter then reads the entire file from top to bottom and runs all the instructions inside it. Script mode is what you'll use for almost all real Python development. It's how you build actual applications, save your work, create reusable pieces of code, automate tasks, and handle anything more complex than a quick one-line test. So the main difference? Interactive mode is for immediate one-off commands and tests. Script mode is for writing saved, complete programs in .py files that you can run whenever you want. Okay, enough theory. Let's actually try running some Python code using both methods. Follow along with me. First, let's try the interactive mode. Open up your terminal or command prompt. If you're not sure how, just search your computer for terminal or command prompt or PowerShell. Now type Python or Python 3 if Python doesn't work, and hit enter. See those symbols? That means we're talking directly to the Python interpreter. Let's try a simple command. Type print testing interactive mode and press enter. See, it immediately prints the text back to us. We can also do math. Try typing 10/2 and press enter. Python calculates it and shows the result, 5.0. We can even create temporary variables. Type x equals 5 and press enter. Nothing seems to happen, but Python now remembers that x holds the value 5. To see it, type print x and press enter. There it is. Cool, right? Now to leave the interactive mode, just type exit and press enter, or quit works too. And we're back to our regular terminal prompt. Okay, part 2, let's try script mode. Open up any simple text editor. I'll use VS Code, but Notepad or TextEdit works fine too. Create a new file. Now let's type a few lines of Python code. First, a comment. Lines starting with hap are ignored by Python. They're just notes for humans. Let's add my first script, py. Then print this message comes from a Python script. On the next line, username, code explorer. Then print hello username. This f string is a handy way to include variables inside text. And finally, print script finished. Now the crucial step, save this file. Go to File, Save As. Make sure you know where you're saving it. Maybe in your C drive, create a new folder called Future Coding Stars. And most importantly, name the file my first script, .py. Don't forget that .py at the end. Click Save. Okay, file saved. Let's go back to our terminal window. Now this is super important. Your terminal is probably open in your home directory. We need to tell it to navigate to the same folder where we just saved our my first script py file. The command for this is cd, which stands for change directory. If you created a future coding stars folder inside your main user folder, you might type cd future coding stars. Once you think you're in the right folder, you can type ls on Mac Linux or dir on Windows and press enter to list the files. You should see my first script.py listed there. Perfect. Now that we're in the right directory, we can run the script. Type python myfirstscript.py and press enter. Look at that. It printed all 3 lines from our script. This message comes from a Python script, hello Code Explorer, and script finished. It ran the whole file. Now, running code, especially scripts, can sometimes lead to errors when you're starting. Let's look at a couple of common ones so you know what to do. Mistake number 1, trying to run the script from inside the interactive mode. If I type Python to get the prompt, and then I type Python my first script, py, boom, syntax error. Why? Because the prompt expects Python code, not commands for the terminal, like Python file name, py. Remember to exit the interactive mode first before running a script command. Mistake number 2, running the script command from the wrong directory. Let me use cd to go up 1 level so I'm no longer in the folder with my script. Now if I try python my first script.py, error again, file not found error. Python is telling us it can't find the file because we're not looking in the right place. Always make sure you use cd to navigate to the correct folder before running the script. And one more thing, forgetting to save your changes. Watch this. I'll go back to my editor, change the last line to print script finished with exclamation marks. Now, without saving, I go back to the terminal and run python my first script, py. See? It still prints the old message without the exclamation marks because the interpreter runs the saved version of the file. You must remember to save your changes in the editor, Control S or Command S is your friend, before you run the script again to see the changes. Let me save it now. And run it again. There we go, the new output. All right, now it's your turn to practice. Here's a small challenge for you. Don't forget the details are also in the description below. Your challenge is to 1, create a new Python script. Call it info.py. 2, inside this script, write 3 separate print statements. The first should print your name. The second should print today's date. You can just write it as text for now, like April 12th, 2025. The third should print a fun fact about Python, like Python is named after Monty Python. 3, save the file and run it from your terminal. Make sure you see all 3 lines printed. 4, as a bonus, try to print the same 3 pieces of information using only the interactive Python mode. Notice how the process feels different. Pause the video here, give it a try, and see how you do. How did the challenge go? Hopefully you got it working. Now, a quick word on making life easier. While using a basic text editor and the terminal works perfectly fine, many developers use something called an Integrated Development Environment, or IDE. Think of tools like VS Code, PyCharm, or Thonny. These combine a powerful text editor, a built-in terminal, and often a simple run button, all in one window. They can make writing and running scripts much quicker. If you plan on doing more Python, exploring an IDE is a great next step. Let's quickly recap what we learned. We learned the 2 essential ways to run Python code. 1, interactive mode, accessed by typing Python in the terminal, gives you the prompt for typing commands one by one, getting immediate results, perfect for quick tests. Script mode, where you write code in Py files and run the whole file from the terminal using Python, your script name, py. This is how you save your code and build actual programs. Knowing when to use each of these modes will really help you as you learn more Python. Remember to check the description for the code, the challenge details, a downloadable cheat sheet, the quiz, and this summary. So we know how to run code now, but what kind of code can we actually write? What can we do with Python? In the very next lesson, we'll dive into the absolute basics, variables and data types. We'll learn how Python stores different kinds of information like numbers and text, which is the foundation for everything else. It's where the real coding begins. Imagine your computer's memory is like a giant warehouse full of empty boxes. If you just put things in random boxes, how would you ever find them again? You need labels. In programming, these labels that help us store and find information are called variables. Or think about filling out an online form. You enter your name, which is text, your age, which is a number, maybe check a box, which is like true or false. These are all different types of data. Python needs a way to understand what kind of data it's working with. So in this video, you'll learn the absolute basics, what variables are and how we create them. The most common types of data you'll use all the time in Python: numbers, text, and true-false values. Why does this matter? Because everything you build in Python, from simple scripts to complex applications, uses variables and data types. They are the fundamental building blocks. So let's get started. Okay, so what exactly is a variable? Simply put, a variable is a named storage location in your computer's memory. Think of it as a labeled box where you can keep a piece of information. You give the box a name, the variable name, and you put something inside it, the value. Its main purpose is to hold data that you might want to use later in your program, or data that might change as your program runs. To put a value into a variable, we use the assignment operator, which is just the equal sign. This might look like math, but in programming, it means assign the value on the right to the variable name on the left. It's like putting the value into the labeled box. For example, if we write player score equals 100, we are telling Python, create a variable named player score and store the value 100 in it. Now, you can't name your variables just anything. There are a few rules and common practices. Variable names must start with an uppercase or lowercase letter, AZ, or an underscore, but they cannot begin with a number. The rest of the name can contain letters, numbers, 09, and underscores. Spaces are not allowed in variable names. Variable names are case sensitive. That means age, and age are three different variables. A common practice in Python is to use snake case for variable names, all lowercase letters with words separated by underscore, like first name or item count. It makes code easier to read. Also, avoid using names that are already Python keywords, like print, if, for, while, etc. Your editor might highlight these differently. Great, we know how to label our boxes, variables. But what about the stuff we put inside? That's where data types come in. A data type tells Python what kind of data a variable holds and what kinds of operations you can do with it. Is it a number you can do math with? Is it text you can display? One cool thing about Python is that it's dynamically typed. This means you don't have to explicitly tell Python what type of data a variable will hold beforehand. Python is smart enough to figure it out automatically based on the value you assign. Let's look at the most common basic data types you'll use constantly. First, we have integers, or int. These are whole numbers. They can be positive, negative, or 0, but they don't have a decimal point. Think counts, scores, or simple whole number values. Next are floating point numbers, or float. These are numbers that do have a decimal point. They're used for prices, measurements, or any value where precision is needed. Then we have strings, or str. Strings represent text. You create them by enclosing characters within either single quotes or double quotes. It doesn't matter which you use, as long as you are consistent for that string. Names, messages, addresses, these are all usually strings. Finally, we have the Boolean type, or bool. This one is simple but powerful. A Boolean can only have one of two values, true or false. Notice the capital T and F. That's important. Booleans are essential for making decisions in your code, like checking if a user is logged in or if a game condition is met. Since Python figures out the type for us, how can we check what type a variable actually holds? We can use the built-in type function. You just put the variable name inside the parentheses, and Python will tell you its type. We'll try this out in a moment. All right, theory is great, but let's actually write some code. Open up your Python environment. You can use IDE or any simple text editor and the terminal. Let's create variables for each type we just learned. Follow along with me. My age equals 30. This is an integer. Item price equal 450. This is a float. Student name equals Bob. This is a string. Is logged in equals true. This is a Boolean. Now let's display the values using the print function. Print my age, print student name, print item price, print is logged in. See, the print function shows us the values stored in our variables. Now let's use that type function we talked about. Print type my age, print type item price, print type student name, print type is logged in. Look at that output. Python tells us the class or type of each variable. Int, float, star, and bool, just as we expected. Variables aren't set in stone. You can change the value they hold. Let's update my age. My age equals 31. Print my new age, my age. You can even change the type of data stored in a variable. This is part of what dynamically typed means. Watch this. Temp var equals 10, print type temp var. Temp var equals now I'm text, print type temp var. See, temp var started as an integer, but then we assigned a string to it and Python automatically updated its type. Pretty flexible. When you're starting out, you'll definitely run into some errors. That's totally normal. Let's look at a few common ones related to variables and data types. Mistake 1, forgetting quotes. What if you forget the quotes around a string? My name equals Alice. Oops, Python gives us an error. It thinks Alice is another variable, but it hasn't been defined. My name equals Alice. Adding quotes fixes it. Print my name. Remember, text needs quotes. Mistake 2, using undefined variables. What if you try to use a variable before you give it a value? Print undeclared var. Name error. Python is saying, I don't know what undeclared var is. You must assign a value to a variable before you can use it. Undeclared vars now I exist. Mistake 3, case sensitivity. Remember, variable names are case sensitive. My var equals 5, print my var, using lowercase v. Another name error. Even though my var exists, my var, all lowercase, does not. Be careful with capitalization. Mistake 4, invalid names. Trying to start a variable name with a number or use invalid characters like hyphens. First place equals gold, or item cost equals 10. You'll get a syntax error. Python doesn't allow names like these. Stick to the naming rules. Start with a letter or underscore. Use only letters, numbers, and underscores. Let's apply what we've learned. We'll create a simple player profile for a game character using variables. We need a name, level, health points, whether they have a special item, and how many items they're carrying. Character name equals Shadow Rider. String for the name. Level equals 15, integer for the level. Health points 88.5. Float for HP could be fractional. Has magic sword equals true. Boolean yes or no. Inventory items equals 3, integer for the count. See how we chose a data type that makes sense for each piece of information? Name is text. Level is a whole number, int. Health can be decimal, float. Having the sword is yes, no, bool. And item count is a whole number, int. Now let's print out this profile neatly. Print player profile. Print character, character name. Print level, level. Print HP, health points. Print has magic sword, has magic sword. Print items and inventory, inventory items. Here are the results. You see the formatted output in the console. Player profile, character, Shadow Rider. Level 15, HP 88.5, has magic sword, true. Items and inventory 3. Awesome. Using variables makes it easy to store, manage, and display this information. If the character levels up or loses health, we just update the corresponding variable. Ready for a small challenge to test your skills? Your task is on the screen. Declare variables to represent a book with the details shown. Then print out both the value and the type for each variable. Pause the video now, give it a try, and then come back to see one possible solution. Welcome back. How did it go? Just a couple of quick things to think about. What happens if you add an integer and a float? Try print 5 plus 2.5. Python often converts the integer to a float for the calculation, resulting in a float. How can you join strings together? This is called concatenation. You can use the plus sign plus to combine strings. Notice we added a space string in the middle. Think about other real-world things you could model with these basic types, maybe a recipe, a bank account, or a weather report. We covered a lot. Let's quickly recap. We learned that variables are named labels for storing data in memory. We use the equals sign to assign values to variables. We explored the fundamental data types: int for whole numbers, float for decimal numbers, star for text, and bool for true or false. Remember, Python figures out the data type for you, and you can always check a variable's type using the type function. Don't forget to check the video description below. You'll find links to all the code snippets used today, the challenge exercise, a downloadable cheat sheet summarizing these concepts, a quick quiz to test your knowledge, and the key takeaways. You now know how to store data inside your program, but how do you get information from the user or show your results to them in a more interactive way? In our next lesson, we'll cover exactly that: basic input and output. We'll learn how to use the input function to get data from the user and explore more ways to use the print function to display information. Have you ever used a program, maybe a game or an app, that asks for your name? Or maybe a calculator that shows you the answer? Ever wondered how computer programs talk to you and how you can talk back to them? How do they ask for information or show you results? Well, today we're going to learn exactly that. This is a super important first step in programming. We'll learn about two key Python tools. First, the print function, which lets your program show information on the screen. Second, the input function, which lets your program ask the user for information and wait for them to type something in. Knowing how to handle input and output is basic, but it's the key to making programs that actually do things with people. All right, first up is showing things on the screen. In Python, the command or function we use for this is called print. It's super simple. To print some text, you just type print, then open parentheses, and inside those, put the text you want to show inside quotation marks, like this. Print hello world. This text inside quotes is called a string. When we run this, look, it prints hello world right to our screen or console. Easy, right? You can also print the value stored in a variable. Remember variables from our last lesson? They store information. So if I create a variable, say message equals Python is fun, I can then print the contents of that variable like this: print message. See, it prints the text that we stored in the message variable. What if you want to print multiple things at once? You can list them inside the print parentheses, separated by commas. For example, let's say name equals Alex and age equals 25. We can write print name, age. Notice that Python automatically puts a space between the items we listed. Now, that comma way works, but sometimes it gets messy. A newer and often cleaner way to mix text and variables in print is using something called f-strings. It sounds fancy, but it's easy. You just put the letter F before the opening quotation mark, and then inside the string, you put your variable names inside curly braces, like this: print F, name, age. This often makes your code much easier to read, especially when you have lots of variables. We'll be using f-strings a lot. Okay, so we know how to make our program talk, but how do we get information from the user? For that, we use the input function. The basic way to use it is like this: username equals input. When Python runs this line, it stops and waits. It shows a blinking cursor in the console, waiting for the user, that's you, to type something and press enter. Whatever you type is then stored in the variable username, then we can print it to see. I typed Bob, pressed enter, and the program stored Bob in username and printed it. Now, just having a blinking cursor isn't very helpful. The user doesn't know what to type. We can make it user-friendly by putting a message inside the input parentheses. This message is called a prompt. It tells the user what you want them to enter. Let's try. Username equals input. Please enter your name. See? Much better. The program printed our prompt message, waited for me to type, and then continued. Now, here's the most important thing to remember about input. It always gives you back text, even if the user types numbers. In programming, we call text data a string. Let's prove it. I'll ask for age. Age s star equals input, enter your age. Then let's print the type of data stored in age star using print type age star. I type the number 30, but look, Python says the type is class str. That str stands for string. It sees 30 as text characters, not the number 30. Why does this matter? Because you can't do math with strings. If we want to treat the user's input as a number, we need to convert it. If we expect a whole number, we can convert the string to an integer using the int function, like this. Age num equals int age star. Now let's check the type of age num. Aha, now it says for integer. We can now do math with age num. We'll see exactly why this is needed in the coding section, and we'll talk a lot more about different data types and math in the next lesson. There's also float for numbers with decimal points. Theory is great, but let's write some code. Open your Python editor and follow along. Remember, if you want to copy the code snippets directly, they're available in the description below, along with all the other resources like the challenge, quiz, and cheat sheet. First, let's make a simple program that asks for the user's name and greets them. Ask the user for their name. The input at function shows the prompt and waits. Username equals input. What is your name? Now greet the user using an f string. We put the username variable inside the curly braces. Print f hello. Username, nice to meet you. Okay, let's run this. Perfect. It took my input and used it in the output message. Now let's see that string issue in action. Let's ask for the user's age and try to calculate their age next year. Ask for age. Age star equals input. How old are you? Try to calculate age next year. This will cause an error. Print, you entered age star. Print. Let's try to calculate age next year. Next year age equals age star plus 1. Problem line. Print next year you will be next year age. I've typed age star equals input. How old are you? Now watch what happens if I try to just add 1 to age star like this. Next year age equals age star plus 1. Remember, input gives us a string. Let's uncomment that line and the print line and run it. Boom. Error. Look closely. Type error can only concatenate star, not int, to star. This message means we tried to add a number, int, to text, star, and Python doesn't know how to do that. It thinks we're trying to join text, not do math. So how do we fix it? We need to convert the string input into an integer before we do math. We use the int function. Ask for age. Age input equals input. How old are you? Get input as string. Convert the string input to an integer. Age num equals int, age input. Use int here. Now we can do math. Next year age equals age num plus 1. Print the result. Print f, okay, you are age num years old. Next year you will be next year age. See? I first get the input into age input, which is a string. Then I create a new variable age num by converting age input using int. Now age num holds the number and we can add 1 to it. Let's run this version. Yes, it worked perfectly. Remember int when you need a whole number from the user. Just a quick recap of common beginner mistakes. Forgetting to put a helpful prompt message inside input, and getting that type error because you forgot to convert the input string to a number using int before doing math. All right, let's put this together into a small project. We'll create a simple user profile collector that asks for a few pieces of information and then prints a summary. First, a nice welcome message. Print simple user profile collector. Print please answer the questions below. Now let's ask for the name. Name is text, so just input is fine. Username equals input. What is your name? Next, age. We want this as a number, so we need input and int. User age equals int, input how old are you? Let's ask for their favorite hobby. This is text again. User hobby equals input. What is your favorite hobby? And maybe the city they live in. Also text. User city equals input. What city do you live in? Great, we've collected all the info. Now let's print a formatted summary using f strings. Print n, your profile summary, makes a new line. Print f name, username. Print f age, user age. Print f city, user city. Print f enjoys, user hobby. Prints a line of 28 dashes for neatness. Print thank you for using the profile collector. Notice how we use f strings to easily include the variables we stored. That \n in the first print just adds an empty line before the summary, and dash times 28 is a little trick to print a separator line. Let's run the whole thing. Look at that. Our program asked questions, stored the answers, converting age to a number, and then printed a nice summary. We took input and produced structured output. Now it's time for you to practice. Here's your challenge. Write a small Python script. It should ask the user for their favorite food, then ask for their favorite drink. Finally, it should print one single sentence combining both inputs, exactly like this. So you like to eat food and drink drink? Sounds delicious? Replace food and drink with the user's actual input. Pause the video now, give it a try, and see if you can make it work. The full challenge text and maybe a hint are also in the description if you need a reminder. If you finish the challenge, awesome! Here are a few extra things to think about or try. What happens if you run the age part of our code again, but type hello instead of a number when it asks for your age? Try it. You'll get a different error, a value error. We'll learn how to handle errors like this later. If you need to get input that might have a decimal point, like a price, e.g. 4.99 or someone's height, you'd use float instead of int to convert the input string. Try using float input, enter a price, play around with the prompt messages in input. How can you make them clearer for the user? Can you print the user profile summary all on one single line instead of multiple lines? Hint, you might need to explore print options or build one long f string. Let's quickly recap. We learned how to show information using print, including how useful f strings are. We learned how to get information from the user using input, remembering that it always gives us a string, and we saw why we often need to convert that string to a number using int if we want to do calculations. So we can get input now, especially numbers. But what can we actually do with them? We'll dive into arithmetic and comparison operators. We'll learn how to do math like addition, subtraction, multiplication, division, and also how to compare values. Is one number bigger than another? Is something equal? This is essential for making programs that can calculate things and make decisions. Ever wondered how Python does math, like adding numbers together? Or how it can compare things like checking if one number is bigger than another? It's all thanks to something called operators. Think of them as special symbols that tell Python to do a specific job, like adding, subtracting, or comparing. In this video, we're going to learn about two main types: arithmetic operators for doing calculations and comparison operators for checking relationships between values. By the end of this lesson, you'll understand how to use these fundamental tools to perform math and make basic checks in your Python code. This is super important for writing useful programs. Ready to unlock these powerful building blocks? Let's dive in. All right, let's start with the theory. Don't worry, we'll keep it simple and quick before we jump into coding. First up, arithmetic operators. These are the symbols you use for mathematical operations. You probably know most of these. We have plus for addition, like 5 plus 3, minus for subtraction, like 10 minus 4, star for multiplication, like 6 times 7. Now, division is a little special in programming. Slash is for standard division. Notice how it always gives you a number with a decimal point, even if it's a whole number result. This is called a float in Python, and if it's not a clean division, you get the full decimal. Sometimes you only want the whole number part of the division. Double slash is for integer division. See? It just gives you the whole number part, ignoring the decimal. This is useful when you only care about how many times one number fits into another. What if you want the leftover amount after a division? A percent is the modulo operator. If you divide 10 by 3, you get 3 groups of 3 with 1 left over. Modulo gives you that 1. This is handy for things like checking if a number is even or odd. A number modulo 2 will be 0 if it's even. And finally, to raise a number to a power, double star is for exponentiation. This is like saying 2 to the power of 3, which is 2 times 2 times 2 equals 8. Just like in regular math, Python follows an order of operations. Think of PEMDAS or BODMAS. Parentheses go first. Great, that covers the math side. Now let's look at how Python compares things. These operators are used to compare values and check if a condition is true or false. Equals is for checking if two values are equal to. Is 5 equal to 5? Yes, so it gives us true. Is 5 equal to 6? No, so it gives us false. Pay close attention here. Double equals is for comparing if two things are equal. Single equals is for assigning a value to a variable. This is a very common mistake for beginners. Not equal is for checking if two values are not equal to. Is 5 not equal to 6? Yes, that's true. Is 5 not equal to 5? No, that's false. They're equal. Greater than is for greater than. Less than is for less than. Greater than or equal to is for greater than or equal to. Less than or equal to is for less than or equal to. The super important thing to remember about comparison operators is that their result always a Boolean value. It's either true or false. These true-false values are the basis for making decisions in our programs, which we'll see in the next video. All right, theory covered. Let's get our hands dirty with some actual coding. Open up your code editor and let's practice. Let's start with arithmetic operators. We'll use a couple of variables. Let's work with these numbers. num1 equals 25, num2 equals 7. Arithmetic operations. Print arithmetic operations. Okay, first, simple addition. Sum result equals num1 plus num2. Print f sum result, using an f string to easily include the variable. There we go, 25 plus 7 is 32. Now subtraction, multiplication, and standard division. Difference equals num1 minus num2. Printf difference, product equals num1 times num2. Printf product. Division float equals num1 divided by num2. Standard division. Printf standard division float. See how the standard division gives us a float result? Now, integer division and modulo. Division integer equals num1 divided by num2. Integer division. Printf integer division integer. Remainder equals num1 modulo num2. Modulo. Print remainder. 25 divided by 7 is 3 with a remainder of 4. Perfect. And exponentiation. Let's do num2 to the power of 2. Power result equals num2 to the power of 2, 7 to the power of 2. Printf power 7 to the power of 2, power result. That works. Now, let's look at the order of operations. What do you think this will print? Order of operations example. Calc1 equals num1 plus num2 times 2. Printf calculation 1, num1 plus num2 times 2, calc 1. Y39 because multiplication happens before addition. 7 times 2 is 14, plus 25 is 39. If we wanted the addition to happen first, we use parentheses. Cal2 equals num1 plus num2 times 2, parentheses first. Print calculation 2, num1 plus num2 times 2, calc 2. Now we get 64 because 25 plus 7 is 32 and 32 times 2 is 64. So parentheses are important. Okay, let's move on to comparison operators. Remember, these give us true or false. Comparison operations. Print comparison operations. Add a blank line for clarity. Age equals 20. Is age equal to 20? Is exactly 20 equal age equals 20? Printf is age exactly 20? Is exactly 20? Yes, it is, so we get true. Is age not equal to 20? Is not 20 equal age not equals 20? Printf is age not 20? Is not 20? No, it is 20, so the result is false. Let's try greater than and less than. Is older than 18 equals age greater than 18? Print is age older than 18 is older than 18 is younger than 25 equals age less than 25. Printf is age younger than 25 is younger than 25. Both are true for age 20. Now, greater, less than, or equal to. Can vote equal age greater than or equals 18? In many places, 18 is the voting age. Printf can age vote greater than or equals 18? Can vote. Gets junior discount equals age less than or equals 12. Example, junior discount age. Print gets junior discount less than or equals 12. Gets junior discount. Correct results based on age 20. Let's look at a common comparison mistake, comparing different data types. What do you think print 5 equals 5 will do? Common mistake, comparing different types. Print is 5 equal to the string 5, 5 equals 5. It prints false. Python is smart enough to know that the number 5 is not the same as the text 5. They are different types of data. Most of the time, trying to compare completely different types like a number and text won't work or will give you false because they aren't the same kind of thing. Another one, comparing numbers with decimals, comparing floats and integers. Print is 10 equal to 10, 0, 10 equals 10.0. This one is true. Python understands that the integer 10 and the float 10.0 represent the same value. This usually works fine for numbers. Finally, a quick look at comparing strings. Python compares strings letter by letter based on their order in the alphabet, or more accurately, their Unicode value. Comparing strings. Print f is apple less than banana, apple less than banana. Print f is apple less than apple, apple less than apple. Capital letters come before lowercase. This shows how string comparison works. Awesome. We've practiced arithmetic and comparison operators in isolation. Now let's see how they work together in a simple, practical example. Okay, time to put these operators to use in a mini project. We're going to write a small script to calculate the body mass index, BMI, and then use comparison operators to make a simple evaluation. BMI is calculated using a formula, weight in kilograms divided by height in meters squared. We'll need arithmetic operators for this. We'll also need to get input from the user. Remember the input function? It always gives us text, a string, so we need to convert that text into numbers. We'll use float for numbers with decimals. BMI calculator. Print BMI calculator. Get input from the user. Remember input gives strings, so we convert to float. Weight kg equal float input, enter your weight in kilograms. The height m equal float input, enter your height in meters. We ask for weight and height and immediately convert the input strings to floating point numbers so we can do math with them. Now, let's calculate the BMI using our operators. Calculate BMI, weight divided by height squared. BMI equals weight kg divided by height m to the power of 2. We use slash for division and to the power of for squaring the height. We put height m to the power of 2 in parentheses to make sure that calculation happens before the division, just like in the formula. Let's print the calculated BMI. Print the calculated BMI. Print f, your BMI is BMI. This part uses an f string again to show the result nicely. Let's try it. I'll put in some example values. Okay, it calculated the BMI. Now let's use comparison operators to make a simple check. Is this a healthy BMI according to a basic range? The typical healthy range is between 18.5 and 25, not including 25. We need to check two things. 1, is the BMI greater than or equal to 18.5? 2, is the BMI less than 25? We can combine these checks. For now, we'll just print the result of each comparison. In the next video, we'll learn how to use these results to make the program do different things. Use comparison operators to check if BMI is in a healthy range. 18.5 to less than 25 is above min healthy equals BMI greater than or equals 18.5. Is below max healthy equals BMI less than 25. Print is BMI greater than or equals 18.5 is above min healthy. Print is BMI less than 25 is below max healthy. Combine them. Is healthy range equals is above min healthy and is below max healthy. Printf is BMI in healthy range, 18.5 to less than 25, is healthy range. We create two Boolean variables, one for each check. Then we print their results. Last line uses the AND keyword, which means both conditions must be true for the result to be true. Let's try those values again. See how we get true or false based on the calculated BMI. This is how we start to build logic in our programs. All the code snippets from this video, including this BMI calculator script, are available for you to download and play with. Check the video description below for the link. You'll also find a challenge, quiz, and other helpful resources there. You've done great learning about these basic operators. Now it's time for you to practice and reinforce what you've learned. Here's a simple coding challenge for you. Write a Python script that 1. Asks the user for the length of a rectangle. 2. Asks the user for the width of a rectangle. 3. Calculates the area of the rectangle, length times width. 4. Checks if the calculated area is greater than 100. 5. Prints the calculated area. 6. Prints true or false based on whether the area is greater than 100. This challenge uses both arithmetic for area and comparison for checking if it's greater than 100 operators, just like we practiced. Hint: remember to convert the user input from strings to numbers, probably using float since dimensions can have decimals. Pause the video, give it a try. The solution is also available in the resources link in the description if you get stuck or want to check your answer. If you're feeling ambitious and want to explore more, look into augmented assignment operators. Symbols like plus equal, add and assign, e.g. x plus equal 5 is same as equals x plus 5. They are just shortcuts, but are used very often. Also, bitwise operators, and or hat, etc., exist for working with the binary representation of numbers, but those are for more advanced topics. Let's quickly recap what we learned. We learned about arithmetic operators for doing calculations in Python. We saw how slash division gives a float and double slash gives a whole number, integer. We covered comparison operators for checking relationships and conditions. Crucially, we learned that comparison operators always result in a Boolean value, true or false. We also briefly touched on the importance of the order of operations and using parentheses. These operators are the fundamental tools that allow our programs to perform calculations and, most importantly, make decisions based on conditions. We'll use the true-false results from comparison operators to control the flow of our programs using conditional statements, like if, elif, and else. This is where your code starts getting really smart. Don't miss it. Ever wonder how your favorite apps or games seem to think and respond to what you do? Like, how does a game know if you won or lost? Or how does an app show you different things based on your age or location? That amazing decision-making power in code comes from something super important called conditional statements. In this video, you'll learn how to make your Python program smart by using the essential tools, if, elif, and else. By the end, you'll be able to write code that can choose what to do based on different situations. Get ready to add powerful logic to your code. Let's dive in. All right, let's start with the basic idea. Think about making decisions in real life. If it's raining, you take an umbrella. If you're hungry, you eat. If it's sunny, you might go outside. Conditional statements in programming work the same way. They let your code check if something is true or false and then run different blocks of code based on the result. The most basic conditional is the if statement. The structure is simple. You type if, then you give it a condition to check, and then you put a colon. Temperature equals 25. If temperature is greater than 20, print it's warm. Look at this example. We have a variable temperature set to 25. The condition is temperature greater than 20. Since 25 is greater than 20, this condition is true. Now, notice the line print, it's warm, is indented. This is super important in Python. Indentation tells Python which code belongs to the if statement. If the condition is true, Python runs the code that is indented below the if. What if the condition is false? Well, that's where else comes in. The else statement is paired with an if. It says, if the if condition is not true, then do this instead. Temperature equals 18. If temperature is greater than 20, print it's warm. Else, print it's not warm. Here, temperature is 18. Is 18 greater than 20? No, that's false. So the code under the if is skipped, and Python jumps to the else block and runs the code there. Just like with if, the code under else must be indented. Else doesn't need a condition because it runs only when the if condition, or all elif conditions, which we'll see next, is false. But what if you have more than two options, like warm, cold, or just right? For that, we use elif. Elif is short for else if. You can have multiple elif statements between an if and an else. Python checks the if condition first. If it's false, it checks the first elif. If that's false, it checks the next elif, and so on. If all if and elif conditions are false, the else block, if it exists, is executed. Temperature equals 22. If temperature is greater than 25, print it's hot. Elif temperature is greater than 20. This is checked. If the first if is false, print it's warm. Else, this runs if both if and elif are false. Print it's cool. In this case, 22 is not greater than 25, so the first if is false. Then Python checks the elif. Is 22 greater than 20? Yes, that's true. So it prints it's warm and skips the else block. Remember, Python stops checking as soon as it finds the first condition that is true. Now, what exactly goes into these conditions? We use comparison operators to compare values. Equal to, not equal to, greater than, less than, greater than or equal to, less than or equal to. These operators compare two values and give you back either true or false. This true or false is exactly what the if, elif statements need. X equals 10, y equals 5, print x equals y. Output, false, print x not equals y. Output, true, print x is greater than y. Output, true. You can see how these comparisons result in true or false. Sometimes you need to check more than one thing at the same time. For that, we use logical operators, and true if both conditions are true, or true if at least one condition is true. Not reverses the result, true becomes false, false becomes true. Age equals 25, has ID equals true. If age greater than or equal 18 and has ID, print you can enter the club. If age is less than 18 or not has ID, print you cannot enter the club. In the first if, both age greater than or equal 18 true and has ID true are true, so true and true is true, and the message is printed. In the second if, age is less than 18 is false, but not has ID, which is not true. So false makes the whole or condition false or false, which is false. Let's change the example slightly. Age equals 16, has ID equals true. If age is greater than or equals 18 and has ID, print you can enter the club, else print you cannot enter the club. Another example with or, is student equals true, is senior equals false. If is student or is senior, print you get a discount. Now age is greater than or equals 18 is false, so the and condition is false and the else runs. In the second example, is student is true. So even though is senior is false, true or false is true, and the message is printed. The not operator just flips the result of a condition. Not true is false and not false is true. Is logged in equals false. If not is logged in, print please log in. This if condition not is logged in becomes not false, which is true, so the message is printed. Okay, we've covered the theory: if, elif, else, comparison operators, and logical operators. Now let's get our hands dirty with some live coding. All right, let's open up our code editor. We'll start simple and build up. First, let's check if a number is positive or negative. We'll ask the user for input. Check positive, negative. Num star equals input, enter a number. Num equals int num star. Convert input string to an integer. If num is greater than 0, print this is a positive number. Elif num is less than 0, print this is a negative number. Else, print this number is 0. We get input, convert it to a number, then we use if to check if it's greater than 0. If not, elif checks if it's less than 0. If neither is true, it must be 0, so the else block runs. Let's run it. Enter 5. This is a positive number. Great. Enter -3. This is a negative number. Perfect. Enter 0. This number is 0. Awesome. It works as expected. Now let's build a simple grading system based on a score. Simple grading system. Score star equals input. Enter the student's score, 0 to 100. Score equals int score star. If score is greater than or equal 90, print grade A. Elif score greater than or equal 80, checked only if score is not greater than or equal 90. Print grade B. Elif score is greater than or equal 70, checked only if score is not greater than or equal 90 and not is greater than or equal 80. Print grade C. Elif score is greater than or equal 60, checked only if previous conditions are false. Print grade D. Else, if none of the above conditions are true, print grade F. See how the elif statements are checked one by one. If the score is 95, the first if score is greater than or equal 90 is true, it prints grade A, and Python skips all the elif and else blocks. If the score is 85, the first if is false, the first elif score is greater than or equal 80 is true, it prints grade B and skips the rest. Let's test it. We see that 92 maps to an A, 85 to a B, 78 to a C, 61 to a D, and 55 to an F. Looks correct. Now, let's look at common errors you might make and how to fix them. If you forget the colon after if, elif, or else, Python will give you a syntax error. See, it says syntax error expected. The fix is simple. Just add the colon. Incorrect indentation. Indentation is crucial. If you don't indent the code block under if, elif, or else, you'll get an indentation error. Python tells you it expected an indented block. Make sure the lines belonging to the conditional block are indented by the same amount, usually 4 spaces. Error 3, using single equals instead of double equals. This is a classic. Single equals is for assigning a value to a variable. Double equals is for checking if 2 values are equal. Using single equals in an if statement condition like this will likely give you a syntax error or unexpected behavior. Python expects a comparison that results in true or false. Always use double equals when you want to check if two things are the same. Error 4, logic errors with and/or operators. Sometimes the code runs, but it doesn't do what you expect because the logic in your and or condition is wrong. Remember our club entry example? If age greater than or equal to 18 and has ID. If you meant they could enter if they are 18 or they have an ID, using and would be a logic error. You need to think carefully about whether both things need to be true or just one of them. The best way to avoid these is to write out the condition in plain English first and then translate it carefully into code. Also, test your code with different inputs that should hit each part of your if, elif, else structure. Now that we've seen how conditionals work and how to avoid common pitfalls, let's use them to build a little project. We're going to create a simple what to wear program based on the temperature and maybe if it's raining. First, we greet the user. Then we ask for the temperature and convert it to an integer, just like before. Next, we ask if it's raining. We take their input, convert it to lowercase using .lower, and check if it's exactly yes. This comparison is raining star, lower equals yes, will give us true if they typed yes or yes, yes, etc., and false otherwise. We store this true-false value in the isRaining variable. This is a neat trick. Now the conditional logic. We start with the coldest case. If temp is less than 0. If it's below 0, it's freezing. The next elif checks if the temperature is less than 10. If the first if was false, this means the temperature is between 0 and 9 degrees. Inside this elif, we have another if-else. This is called a nested conditional. It means we make another decision inside the first one. If the temperature is between 0 to 9 and it's raining, if is raining, we give one suggestion. Else, if it's not raining, we give another. We repeat this pattern for temperatures less than 20, meaning 10 to 19 degrees. Finally, the else block at the end catches anything that wasn't less than 20, meaning 20 or higher. Again, we check if it's raining inside this else block. Let's run this. Temp -5, not raining, it's freezing. Temp 5, raining. It's cold and wet. Temp 15, not raining. It's cool. A sweater. Temp 25, raining. It's warm but raining. It seems to work. This simple program shows how you can combine if, elif, and else, and even nest them to create more complex logic in your programs. You've done great so far. Now it's time to practice and stretch your skills. Your challenge: write a Python program that asks the user for a year and tells them if it's a leap year. Remember the rules for a leap year. A year is a leap year if it is evenly divisible by 4, except years divisible by 100 are not leap years unless the year is also evenly divisible by 400. You'll need to use the modulo operator to check for even divisibility, e.g. year modulo 4 equals 0, and you'll definitely need an and or in your conditional statements. This little formula should help you structure your main condition. Think about how to put that into an if-else structure. You can find the exact challenge code and input-output examples in the description below, along with starter code to help you get started. For those who want to explore further, how would you handle someone typing in text instead of a number for the year? You might need try and accept blocks, which is a more advanced topic for handling errors. Research Python's match statement, available in Python 3, 10, and later. It's a newer way to handle multiple choices that can sometimes be cleaner than many elif statements. Wow, you've learned a ton about making decisions in your code today. Let's quickly recap. Conditional statements, if, elif, else, allow your programs to choose which code to run based on conditions. Conditions are statements that evaluate to either true or false. We use comparison operators like equals, greater than, less than, etc. to create conditions. We use logical operators and or not to combine or modify conditions. Indentation is critical in Python to define the code blocks under if, elif, and else. You've just unlocked a fundamental way to control your program's flow and make it much more dynamic and useful. Now, making decisions is powerful, but what if you want your program to repeat actions, like do something 10 times or do something until a certain condition is met? That's where loops come in. You're going to learn everything about repeating tasks in Python. mastering for loops, while loops, and controlling them with break and continue. Tired of writing the same lines of code over and over again? Imagine you need to do something like process a list of 1,000 customer names, or maybe keep asking a user for their password until they get it right. Manually coding each step for every single item? That sounds like a programmer's nightmare. That's exactly where the superpower of loops comes in. Loops are the absolute backbone of making your code efficient, automated, and frankly, much easier to write. In this video, we're going to unlock the two main types of loops in Python, the for loop and the while loop. Plus, you'll learn how to get ultimate control over your loops using break and continue. By the end of this lesson, you'll be writing Python code that can repeat tasks effortlessly, saving you tons of time and effort. All right, let's dive into the theory. So at its core, why do we use loops? Simple. They let us run a block of code multiple times without having to write that block over and over again. Think of it as giving your computer a set of instructions and saying, do this X times, or do this until something specific happens. Let's start with the for loop. The for loop is perfect when you know exactly how many times you want to repeat something, or more commonly when you want to go through each item in a sequence. What kind of sequences? Well, things like lists of names, strings, which are sequences of characters, tuples, and even dictionaries. These are all types of iterables in Python, things you can loop over item by item. The basic structure looks like this. For item in sequence, code to repeat for each item, print item. You can read this as, for each item in this sequence, do the code indented below. Names equals Alice, Bob, Charlie. For name and names, print hello plus name. See? It went through each name in the list and printed a greeting. Super handy. What if you just want to repeat something a specific number of times and you don't have a list? That's where the range function comes in. Range gives you a sequence of numbers. For example, range 5 gives you numbers 0, 1, 2, 3, 4. For I in range 5, this will print 5 times. You can also give range a start and stop number, like range 16, which gives you 1, 2, 3, 4, 5. Remember, range stops before the end number. This is a common spot for a small mistake, often called an off by 1 error. If you want numbers 1 to 5, you need range 16. Okay, that's the for loop, great for iterating over things or repeating a fixed number of times. Now let's look at the while loop. The while loop is different. It repeats a block of code as long as a certain condition is true. You don't necessarily know ahead of time how many times it will run. The structure is, while condition, code to repeat while the condition is true, print, still looping. Important, update the condition variable here. Here the condition is something that can be either true or false, like x10 or is game over equals false. Count equals 0, while count is less than 3, print count is count. Count equals count plus 1, or count plus equals 1. In this example, count is less than 3 is the condition. The loop keeps running as long as that's true. Critical point alert. With while loops, you must make sure that the condition will eventually become false. If the condition never changes or never becomes false, you'll get an infinite loop. Your program will just keep running forever and likely freeze. Danger infinite loop. X equals 5, while x is greater than 0, print help, I'm stuck. The value of x never changes. Condition is always true. See, x is greater than 0 is always true because x stays at 5. To fix this, you need to change x inside the loop, like subtracting from it so it eventually reaches 0 or less. Fix loop x equals 5, while x is greater than 0, print counting down x. X equals x minus 1, or x minus equals 1. Phew, much better. Always remember to update your condition variables in while loops. Loops are powerful, but sometimes you need more control within the loop itself. That's where break and continue come in. The break statement is like an emergency exit. When Python hits break inside a loop, it immediately stops the loop completely and the program continues with the code after the loop. Use break when you've found what you're looking for or a certain event happens that means the loop should stop early. Numbers equals 1, 5, 8, 12, 7, 15. Search 4 equals 7 for num in numbers. Print checking num. If num equals search for, print found at search for. Break exit the loop now. Print not found yet. This line is skipped after break. Notice how it printed checking 7, then found it, and then stopped. It didn't check 15 because break exited the loop. The continue statement is different. It's like skipping a step. When Python hits continue inside a loop, it stops the current iteration and jumps straight to the next one. The rest of the code below continue in that iteration is skipped. Use continue when you want to skip processing for a specific item or condition, but still want to keep the loop running for the other items. Numbers equals 1, 2, 5, 8, 10. For num in numbers, if num is less than 0, print skipping negative number num. Continue. Skip the rest of this iteration. Print processing positive number num. See how it said skipping negative number for -2 and -8, but didn't print processing positive number for them? It just jumped to the next number in the list. Understanding when to use for versus while and how break and continue can change how your loops run is absolutely key to writing powerful and effective loop logic in Python. All right, enough theory. Let's get our hands dirty and write some code together. Open up your favorite code editor and follow along. First, let's play with for loops. Let's create a list of numbers and print each one. For loop iterating through a list, numbers list equals 10, 20, 30, 40, 50. Print iterating through a list. For number in numbers list, print number. Simple, right? It goes through every item in the list. How about a string? Strings are just sequences of characters. For loop iterating through a string, my string equals Python. Print n iterating through a string. For char in my string, print char. Prints each character on a new line. Now using range to repeat something a specific number of times. Let's print numbers from 1 to 10. Remember, range start stop stops before stop, so we need range 111. For loop with range, print n using range 111. For I in range 111, print I. Perfect. What about dictionaries? We can iterate through them too. By default, a for loop on a dictionary iterates through its keys. For loop iterating through a dictionary, my dict equals apple 1, banana 2, cherry 3. Print n iterating through dictionary keys. For key in my dict, print key. To get keys and values, use the items method. Print iterating through dictionary items key value. For key value in my dict items, print key value. Great, we've covered the basics of for loops. Let's move on to while loops. Let's build that simple counter loop we saw earlier. Simple while loop counter. Count equals 0, print simple while loop. While count is less than 5, print count, count. Count equals count plus 1. Increment the counter. See how count goes from 0, 1, 2, 3, 4. When it becomes 5, the condition count 5 is no longer true, and the loop stops. Now let's try a slightly more practical example, simulating a login attempt with a limited number of tries. While loop for login attempts, correct password equals secure 123, attempts equals 0, max attempts equals 3, print login simulation 3 attempts max. While attempts is less than max attempts, user input equals input, enter password, get user input. If user input equals correct password, print login successful. Break, exit the loop because we succeeded. Else, print incorrect password. Attempts equals attempts plus 1. Increment the attempt counter. After the loop finishes, if attempts equals max attempts, print too many failed attempts. Account locked. Notice how we used break there? As soon as the user enters the correct password, we don't need to loop anymore, so break gets us out. If attempts reaches max attempts, the while attempt is less than max attempts condition becomes false and the loop stops naturally. and then we check if they ran out of attempts. This is a great example of using a while loop when you don't know how many tries it will take, but you have a clear stopping condition, either success or running out of attempts. Let's see break and continue in action more specifically. Back to our number list. Let's use break to stop the loop as soon as we find the number 7. Using break in a loop, numbers list equals 1, 5, 8, 12, 7, 15, 20. Search for equals 7. Print, using break to stop when 7 is found. For number in numbers list, print checking number. If number equals search for, print found 7, stopping the search. Break, exit the loop. This line won't run after break. Print still looking. Print loop finished. This line runs after the loop exits. See? Still looking. Wasn't printed after 7 was found because break instantly jumped out of the loop. Now, let's use continue to skip even numbers and only print the odd ones. Using continue in a loop, numbers list equals 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Print using continue to skip even numbers. For number in numbers list, if number modulo 2 equals 0, check if the number is even. Print skipping even number. Continue. Skip the rest of the code in this iteration. This line only runs for odd numbers. Print processing odd number. Notice how processing odd number only prints for the odd numbers. When the number was even, continue sent us straight to the next number in the list. You can use break in while loops too. Let's make an intentional infinite loop and use break to escape it based on user input. Break in a while loop with potential infinite loop if condition is never met. Print n using break in a while loop. While true, this condition is always true. Potential infinite loop. User input equals input, type quit to exit. If user input dot lower equals quit, print exiting loop. Break. This break is our escape route. Print, you typed user input. Print, program continued after the while loop. This while true, loop would run forever if we didn't have that if statement checking for quit and the break inside it. It's a common pattern for programs that need to run continuously until a specific exit command is given. See how these tools, break and continue, give us fine-grained control over exactly when and how our loops repeat? They are super useful. Before we move on, let's quickly touch on common mistakes and how to think about debugging loops. We already saw the most critical one for while loops, the infinite loop. If your program freezes or a loop runs forever unexpectedly, check your while loop condition and make sure you're updating the variables involved so the condition will eventually become false. Another common one is the off by 1 error, especially with range or loop conditions. Remember, range start-stop includes start but excludes stop. If you want to process exactly 5 items using range, you'd typically use range 5, which gives 0, 1, 1, 2, 3, 4, or range 1, 6. Pay close attention to the is less than or equals versus is less than or is greater than or equals versus is greater than in your while loop conditions to make sure you include or exclude the boundary values correctly. If a loop isn't doing what you expect, try adding print statements inside the loop to see the value of your loop variables like count, item, I at each step. This helps you track the flow and see where it's going wrong. If you're using an IDE like VS Code or PyCharm, you can also learn to use the debugger to step through your code line by line, which is incredibly powerful for understanding loop execution. We won't go deep into debugging right now, but just know that tool exists and is your friend. All right, we've learned the theory and practiced with hands-on examples. Now, let's see how loops can be used to build something useful. We're going to create a simple text-based menu system. The idea is that the program will keep showing the user a menu of options and do something based on their choice, repeating until they specifically choose to quit. This is a perfect job for a while loop, simple menu system project. This variable will control our loop. Run equals true. Print, welcome to the simple menu system. Start the main loop while running. print n menu, print 1, say hello, print 2, say goodbye, print 3, quit. Get user input, user choice equals input, enter your choice 1, 2, or 3. Now check the user's choice using if, elif, else. If user choice equals 1, print hello. Elif user choice equals 2, print goodbye. Elif user choice equals 3, exiting the program. Running equals false. Set the condition to false to stop the loop. Else, print invalid choice, please try again. Print program finished. This runs after the loop stops. Let's walk through this. We start with a variable running set to true. Our while running loop will keep going as long as this variable is true. Inside the loop, we print the menu, get the user's input, and then use if, elif, else to check what they typed. If they choose 1 or 2, we print a message. If they type something else, we print an error, and the loop continues because running is still true. The magic happens when they choose 3. We print an exit message, and then we set running equals false. The next time the while loop checks its condition, running is false, so the loop stops and the program finishes. You could easily extend this, add more options, perform calculations, ask for more input based on the choice. The while loop keeps the program interactive and running until the user wants to stop. You've done great work following along. Now, it's your turn to put your loop skills to the test. Coding challenge. Your task is to write a Python program that takes a list of numbers. Use a loop to calculate the sum of only the positive numbers in the list. Think about which loop is best suited for going through a list, and how can you skip adding the negative numbers to your sum. Hint, remember that continue statement? Pause the video right now and give it a try. Coding is all about practice. Welcome back. How did it go? Don't worry if you didn't get it right away. The process is what matters. You can find the solution code for this challenge linked in the description below, along with all the other code snippets from this video. And if you want to keep exploring, here are a few extension ideas. 1. Look up the else block that can be used with loops. What happens when a loop finishes normally, without a break, compared to when it's broken out of? 2. Explore nested loops. That's loops inside loops. They're powerful for working with grids or combinades or combinations. 3. How would you use loops, maybe even nested loops, to count how many times each character appears in a string? Don't stop here. Practice these concepts, try these challenges, and see where loops can help you solve problems. All right, we covered a lot of ground today. You've taken a huge step in mastering repetition and automation in Python. We learned how for loops are perfect for iterating over sequences like lists or strings, and how range lets you repeat code a specific number of times. We explored while loops, which repeat based on a condition being true, and crucially, we learned to avoid infinite loops by updating that condition inside the loop. You saw how break acts as an emergency exit, letting you stop a loop instantly when a specific event occurs, and how continue lets you skip processing for the current item or situation and jump to the next iteration. You also saw how putting these together allows you to automate repetitive tasks and build simple interactive programs like our menu system. Loops are one of the most fundamental concepts in programming, and you will use them constantly in your Python journey. Speaking of journeys, we're going to dive into working with strings, that essential data type you often use loops with. We'll explore how to manipulate strings, split them, join them, and much more. You might think you can easily change a letter inside a word in Python, but the surprising truth about strings could break your code if you don't know it. Ever wonder how Python handles all the text data we see everywhere, from websites to messages to user inputs? Strings are the fundamental building blocks. Discover the one fundamental rule about Python strings that trips up almost every beginner and how to avoid it. In this video, you're going to learn the absolute basics of Python strings, how to create them, understand their structure, pull them apart, and combine them. Get ready to add a crucial skill to your Python toolkit. In this first part, we'll cover creating strings, understanding how to access characters using indexing and slicing, basic operations, and a really important concept called immutability. Let's dive in. So what exactly is a string in Python? Think of a string as a sequence of characters. It's how Python stores and handles text data, words, sentences, even just letters and numbers mixed together. If you type letters inside quotes, Python sees it as a string. Creating strings is easy. You can use single quotes, like this, or double quotes, like this. Python treats single and double quotes the same for simple strings. It's mostly a matter of style. However, double quotes are useful if your string contains a single quote, like in a contraction. See how the double quotes let us use the single quote inside without confusing Python? The same works the other way around. Now, what about strings that span multiple lines, like a paragraph? For that, we use triple quotes, either 3 single quotes or 3 double quotes. Long text equals, this is the first line, this is the second line, and this is the third. Triple quotes are great for documentation strings, doc strings, or storing blocks of text. Let's do a quick hands-on demo of creating and printing these. Creating strings, single Q equals using single quotes, double Q using double quotes. Quote in string equals, he said, Python is fun. Multi-line string equals. This is a string that spans multiple lines. Printing strings, print single Q, print double Q, print quote in string, print multi-line string. Easy, right? That's the foundation. Now, strings are sequences, meaning the characters are in a specific order. We can access individual characters using something called indexing. Python uses zero-based indexing, which means the first character is at index 0, the second at index 1, and so on. We use square brackets after the string or variable name to access an index. My word equals Python. Print my word 0, access the first character. Print my word 1, access the second character. Print my word 5, access the last character, index 5 for a 6-letter word. You can also use negative indexing. This counts from the end of the string. The last character is at index -1, the second to last at -2, and so on. This is super handy if you want to grab the last character without knowing the string's exact length. Print my word -1, access the last character. Print my word -2, access the second to last character. Print my word -6, access the first character, index -6 for a 6-letter word. What happens if you try to access an index that doesn't exist? Print my word 10. This will cause an error. If you tried to access my word 10, Python would give you an index error because index 10 is outside the range of our 6-character string. Always make sure the index is valid. Indexing gets 1 character, but slicing lets you get a sequence of characters, a substring. The syntax is start, stop. My sentence equals hello Python coders. Print my sentence 0:5. Get characters from index 0 up to, but not including, index 5. Print my sentence 6:12. Get Python. Print my sentence 5. If start is missing, it starts from the beginning, index 0. Print my sentence 13:. If stop is missing, it goes to the end. Print my sentence : If both are missing, it gets the whole string, creates a copy. Remember, the stop index is exclusive. Python goes up to that index, but does not include the character at the stop index. This is a common point of confusion, so practice it. This is a crucial concept. Strings in Python are immutable. This means once a string is created, you cannot change individual characters within that exact string object. Greeting equals hello. Try to change the first character, this will fail. Greeting 0 equals J. If you uncommented that line and ran it, you'd get a type error. Python is telling you you can't change item 0 of this string object. When you perform operations that look like they're changing a string, like replacing a word, Python is actually creating a brand new string in memory with the changes, and your variable then refers to this new string. The original string remains unchanged until Python's memory management cleans it up if nothing else is using it. Greeting, hello. Correct way to change it, create a new string. New greeting equals J, greeting 1, print greeting. Original string is unchanged, print new greeting. This is the new string. See? We didn't change the original hello, we built a new string jello and stored it in a new variable. This immutability is important to understand for how Python handles strings. Even though strings are immutable, we can still easily combine them or repeat them using simple operators. Concatenation means joining strings together, and we use the plus sign. Part 1 equals Python, part 2 equals is, part 3 equals awesome. Full sentence equals part 1 plus part 2 plus part 3. Print full sentence. Name equals Alice. Greeting MSG equals hello plus name plus exclamation mark. Print greeting MSG. You can also repeat a string using the multiplication sign and a number. Separator equals equal times 20. Print separator. Excited word equals wow times 3. Print excited word. Simple and powerful for quickly building or formatting strings. We've covered the absolute essentials: how to create strings using different quotes, how to grab specific characters or sections with indexing and slicing, why strings can't be changed in place, immutability, and how to join or repeat them. You've built a solid base, but there's so much more we can do with strings using Python's built-in tools called methods. In part 2 of this string lesson, we'll dive into these powerful methods to easily change casing, find words, replace text, clean up spaces, and much more. We'll also apply everything we've learned by building a small project to process user input. Make sure you're comfortable with creating, indexing, and basic slicing before moving on. Practice with the code examples from this video. Did you know you can reverse a string in Python with just 3 characters? Can you guess how? Welcome back to our Python strings journey. Did you know a vast percentage of the data you interact with online every day, from emails and tweets to website content, is text? Mastering string methods isn't just a Python skill. It's essential for processing the digital world around us. Python strings come with a bunch of pre-built tools called methods. Think of them as functions attached to the string itself that perform specific actions on it. We call them using the dot notation, string variable dot method name. My string equals hello Python coders. First, let's quickly revisit slicing with a step, which we didn't cover in part 1. The full slicing syntax is start, stop, step. Step tells Python how many characters to skip. The default step is 1. Slicing with step. Print original my string. Print every second character : 2 my string : 2. Start to end. Step 2. Print every second character from index 1 : 2 my string : 2. From index 1 to end. Step 2. A cool trick: reversing a string using slicing. Print reverse string : :-1 my string : -1. Start to end, step -1, backwards. That : :-1 is a common Python trick for reversing strings. The len function, not a method but essential for strings. Print f length of the string, len my string. Okay, now on to the methods. We'll start with changing the case of letters. Case changing methods. Print f original my string. Print f.upper my string to upper. Converts all characters to uppercase. Print f.lowerMyString.lower converts all characters to lowercase. Print f, capitalize, my string, capitalize. Capitalizes the first character, rest lowercase. Print f.title, mystring.title. Capitalizes the first character of each word. Notice that none of these methods changed the original myString. They returned a new string with the changes, just like we talked about with immutability in part 1. One tiny mistake can crash your whole program, and it's hiding inside the index method. Finding substrings. Text to search equals Python is a powerful programming language. Python is fun. Print f original text to search. .find returns the lowest index where the substring is found, or -1 if not found. Print index of Python using find, text to search, find Python. Printf index of Java using .find, text to search .find Java, not found, returns -1. Index, similar to find, but raises a value error if the substring is not found. Print f index of powerful using index, text to search index, powerful. Potential error, substring not found with .index. Print f index of Ruby using Ruby. Uncommenting this will cause a value error. Use .find when you just want to check if something exists and don't want the program to crash if it's not there. Use .index if you expect the substring to be there and it's okay for the program to stop if it isn't. Replacing substrings. Bad sentence equals this is a bad and terrible sentence. Print original bad sentence. Replace old new. Replaces all occurrences of old with new. Good sentence equals bad sentence. Replace bad, good. Replace terrible, great. Print f.replace good sentence. You can limit the number of replacements. Duplicate words equals hello, hello, hello. Print f original, duplicate words. Dot replace old new, count replaces count number of occurrences. Single hello equals duplicate words, dot replace hello, h high 1. Print replace single hello. The replace method is incredibly useful for cleaning up text or making substitutions. Removing leading, trailing white space. Messy string, lots of spaces around. Print original, messy string. Use quotes to show the spaces. Print f, strip, messy string, strip. Remove spaces from both ends. Print f l strip, messy string l strip. Remove spaces from the left leading. Printf r strip, messy string r strip. Remove spaces from the right trailing. Can also remove specific characters from ends. Dotted string equals hello world. Print f original dotted string. Print f strip dotted string strip. Strip is your best friend when dealing with user input that might have extra spaces. Checking prefixes and suffixes. File name equals document PDF. Print file name, file name. Print f starts with doc, file name starts with doc. Check if string starts with doc. Print ends with .pdf, file name ends with .pdf. Check if string ends with .pdf. URL equals https www.example.com. Print URL. Printf dot starts with URL, starts with HTTP. Printf starts with HTTPS. URL starts with HTTPS. These are great for checking file types, URLs, or other specific patterns at the beginning or end of a string. There are many more string methods. Two important ones you'll see often are split, which breaks a string into a list of words or parts, and join, which does the opposite, combines a list of strings into a single string. We'll cover these more when we talk about lists in the next lesson. We've just covered some of the most common and useful string methods. Practice using them. The best way to learn is by doing. Let's put some of these methods to work in a small project. We'll create a script that takes a sentence from you, the user, and does a few things with it. First, we need to get input from the user. We use the input function for this. Print simple input processor, user sentence equals input, please enter a sentence. Handle potential empty input. If not user sentence, print you didn't enter anything. We could exit or loop. For this simple demo, let's just stop here. Exit exits the script. Good practice to check if the user actually typed something. Now let's make sure we process the text in a consistent way, regardless of how the user typed uppercase or lowercase letters. We'll convert the whole sentence to lowercase. Convert to lowercase for easier processing. Processed sentence equals user sentence dot lower. Print f original sentence user sentence. Print f lowercase sentence processed sentence. How long is the sentence? We can find that using the len function. Find the length of the sentence. Sentence length len user sentence or len processed sentence. Length is the same. Printf length of the sentence, sentence length, characters. Next, let's check if a specific word, say Python, is present in the sentence. We can use find or the in operator. Using in is often simpler for just checking presence. Check if a word is present using in operator. Search word equals Python. Check for lowercase Python because we lowercase the input. If search word in process sentence, print yes, the word search word is in the sentence. Else, print no, the word search word is not in the sentence. Alternative using .find. If process sentence find search word not equal -1, print yes, the word search word is in the sentence using find. Finally, let's try to replace a word if it appears. Let's say we want to replace any mention of bad with good. Replace a word, example, replace bad with good. Word to replace equals bad. Replacement word equals good. Modified sentence equals processed sentence. Replace word to replace. Replacement squirt word. Print F sentence after replacing word to replace with replacement word modified sentence. Let's put it all together in one script and add some clear output. Great, we've used input, lower, len, the in operator, and .replace to build a simple text processor. This shows how you can combine these tools to work with real-world text data. Time for a challenge to test your understanding, especially of slicing and maybe case sensitivity. A palindrome is a word, phrase, number, or other sequence of characters that reads the same backward as forward, like level or madam. Your challenge is to write Python code that takes a word or phrase and checks if it's a palindrome. Hint: remember that cool slicing trick for reversing a string? Compare the original, maybe after cleaning up spaces or changing case, with its reverse. Want to explore further? Check out the dot count method, which tells you how many times a specific substring appears in a string. For more advanced text processing, you might look into the string module or even the powerful world of regular expressions, regex, though that's a bigger topic for later. Wow, you've learned a ton about Python strings. In this video, we mastered essential string methods like changing case, finding and replacing text, stripping spaces, and checking starts ends. We also put these skills to use in our simple user input processor project. Understanding how to work with strings is vital because text data is everywhere in programming. You now have powerful tools to handle it. We've dealt with sequences of characters, strings, but what about handling collections of different types of data, like a list of names, ages, or prices? That's where lists come in. In the next video, we'll explore lists and all the amazing operations you can perform on them. It's another fundamental Python data structure you need to know. Don't forget to check the description below for all the resources. The code snippets from this video, the palindrome checker challenge, suggested extensions, a downloadable summary, and a quiz to test your understanding of string methods and the project. Imagine the power of handling any list of information, from names and numbers to complex objects, all within one neat structure. That essential power is unlocked starting right now. We're starting a journey into one of Python's most essential tools, lists. By the end of this video, you will confidently create Python lists, access specific items using powerful techniques like indexing and slicing, and perform basic operations that make data management a breeze. Have you ever needed to keep track of a collection of things in your code? Like maybe a shopping list, a list of your favorite movies, or even a series of numbers from some data? Trying to manage each item with its own separate variable would be a total mess. Imagine having 1 equals milk, item 2 equals eggs, item 3 equals bread, and so on for 100 items. That sounds like a nightmare. This is exactly why Python gives us lists. They are super useful containers that let you store and manage multiple items all in one place. Mastering lists is fundamental to writing clean and efficient Python code, and we're breaking it down into easy steps starting right now. Let's jump in. Python lists are ordered, meaning the items stay in the order you put them in, and each item has its own position. They are also mutable, but we'll talk more about what mutable means and why it's cool in a later video when we learn how to change lists. For now, just know you can change them. A really powerful thing about Python lists is that they can hold items of different types. You can have text, strings, numbers, integers, or decimals, true-false values, booleans, and even other lists, all in the same list. And how do you recognize a list in Python code? Simple. They are always defined using square brackets with the items inside separated by commas. Creating lists is super easy. The simplest way is to just use square brackets. To make an empty list, you just use empty square brackets. You can fill it up later. To make a list with some items already in it, you put the items inside the square brackets separated by commas. Here's our fruits list again. You can create lists of numbers or mixed data types, as we saw earlier. There's also a built-in function called list that you can use to convert other things into a list, like a string. This turns each character into an item in the list. We won't use this too much right now, but it's good to know it exists. Okay, now that we have lists, how do we get to a specific item inside the list? This is where indexing comes in. Remember that lists are ordered? Python gives each item a position number, starting from 0 for the first item. This is called zero-based indexing. So the first item is at index 0, the second at index 1, the third at index 2, and so on. Fruits equals apple, banana, cherry. First fruit equals fruits 0. Second fruit equals fruits 1. Third fruit equals fruits 2. Print first fruit. Print second fruit. Print third fruit. To access an item, you use the list's name followed by square brackets containing the index number. Like fruits 0 gives us apple. What if you try to access an index that doesn't exist? Fruits equals apple, banana, cherry. This will cause an error. Fourth fruit equals fruits 3. Print fourth fruit. If you try to access, say, index 3 in our fruits list, which only has indices 0, 1, and 2, Python will give you an index error. This error message, list index out of range, simply means you asked for an item at a position that doesn't exist in the list. So always make sure the index is valid. Python also has a cool feature called negative indexing. This lets you count from the end of the list. The last item is at index -1, the second to last is -2, and so on. Fruits equals apple, banana, cherry. Last fruit equals fruits -1. Second last equals fruits -2. Print last fruit. Print second last. This is super handy when you just want to get the last item without knowing exactly how long the list is. What if you want a part of the list, not just a single item? That's where slicing comes in. Slicing lets you get a sublist. Fruits equals apple, banana, cherry, date, elderberry. Indices 0, 1, 2, 3, 4. Slicing uses a colon inside the square brackets like list, start, stop. Fruits equals apple, banana, cherry, date, elderberry. Slice 1 equals fruits 1, 3. Gets items from index 1 up to, but not including, index 3. Print slice 1. The start index is where the slice begins and is included, and the stop index is where the slice ends, but it is not included. This is a common point of confusion for beginners. The stop index is exclusive. Fruits equals apple, banana, cherry, date, elderberry. Slice from start equals fruits 2. Gets items from the start up to index 2, not including. Slice to end equals fruits 3, gets items from index 3 to the end. Copy of list equals fruits gets a copy of the whole list. Print slice from start, print slice to end, print copy of list. You can leave the start or stop blank. Leaving the start blank means start from the beginning. Leaving the stop blank means go to the end. Using just a colon gives you a copy of the entire list. There's also an optional third number in slicing called the step. This tells Python how many items to skip. Fruits equals apple, banana, cherry, date, elderberry. Slicing with a step, optional third number. Every other equals fruits 2. Start at beginning, go to end, skip every other item, print every other. 2 means start at the beginning, go to the end, but take every second item. Super flexible. Lists have some built-in operations and functions that are really useful. Fruits equals apple, banana, cherry. List length equals len fruits. Print number of fruits, list length. You can find out how many items are in a list using the len function. Len fruits gives us 3 because there are 3 items. List 1 equals 1, 2. List 2 equals 3, 4. Combined list equals list 1 plus list 2 concatenation. Print combined list. You can join 2 lists together using the plus operator. This is called concatenation. It creates a new list containing all items from both lists. 0 list equals 0 times 5, repetition. Print 0 list. You can repeat a list or a single item list like 0 multiple times using the repetition operator. 0 times 5 creates a list with the number 0 repeated 5 times. Fruits equals apple, banana, cherry. Is apple there equals apple in fruits. Membership check. Is grape there equals grape in fruits. Print is apple in the list. Is apple there. Print is grape in the list. Is grape there. You can check if an item exists in a list using the in keyword. It returns true if the item is found and false otherwise. All right, we've covered the absolute basics of Python lists. We learned that lists are ordered containers using square brackets that can hold different types of data. You learned how to create lists, access individual items using positive and negative indices, and get sections using slicing. We also saw how to find the length of a list, combine lists, repeat lists, and check if an item is inside a list. We also touched upon the index error you might encounter. This is just the beginning. Lists are powerful because they are mutable, meaning you can change them. In part 2 of this series, we're going hands-on and learning how to modify lists by changing, adding, and removing elements. You'll see methods like append, insert, remove, pop, and del in action. Ready to go beyond the basics? If you want to change your lists after you create them, you're in the right place. That's the power of being mutable. 100% hands-on code. We're covering all the key ways to add, remove, and update your list items. Let's jump in and start modifying. Okay, let's start with a simple list like our fruits list from last time. Fruits equals apple, banana, cherry. Print original list, fruits. Print first item, fruits 0. Print last item, fruits -1. Just a quick recap on accessing elements. Remember, we use the index in square brackets. Print slice from index 1 to the end, fruits 1:. And slicing gets a portion of the list. Now, let's talk about changing an existing item. Suppose we want to change banana to blueberry. Banana is at index 1. Fruits equals apple, banana, cherry. Recreate list for fresh start. Fruits 1 equals blueberry. Change item at index 1. Print after changing index 1, fruits. See, we just access the item using its index fruits 1, and then use the assignment operator equals to give it a new value. Simple as that. You can change any item this way as long as the index exists. Now, how do we add new items to a list? There are a couple of common ways. The most frequent is using the append method. Fruits equals apple, blueberry, cherry. Start with our modified list. Fruits.append date, add date to the end. Print after appending date, fruits. The append method adds the new item to the end of the list. It's like adding something to the bottom of your shopping list. You just use listname.append item to add. Fruits.append blueberry can add duplicates. Print after appending blueberry again, fruits. You can append any type of item, even duplicates or another list, though appending a list adds the list itself as a single item, not its contents. We'll cover extend later. Fruits equals apple, blueberry, cherry, date, reset for clarity. Fruits.insert1 banana, insert banana at index 1. Print after inserting banana at index 1, fruits. Insert takes two arguments, the index where you want to insert the item and the item itself. Fruits.insert1 banana puts banana at index 1, and everything that was originally at index 1 and beyond gets shifted one position to the right. Fruits.insert0 kiwi, insert at the beginning. Print after inserting kiwi at index 0, fruits. You can insert at any valid index. If you use an index larger than the list's current size, it behaves like append and adds it to the end. Okay, adding is done. Now, how do we take items out of a list? Python gives us a few ways depending on how you want to remove. Let's start with remove. This method removes the first occurrence of a specific value you provide. Fruits equals kiwi, apple, banana, blueberry, cherry, date, use current list. Fruits.remove banana, remove the value banana. Print after removing banana, fruits. It found banana and took it out. What happens if you try to remove a value that isn't in the list? This will cause an error. Fruits.remove grape. Print after trying to remove grape, fruits. If the item you try to remove isn't found, Python throws a value error. The error message x not in list tells you exactly what went wrong. The value you tried to remove wasn't there. You might want to check if an item is in the list using in before trying to remove it if you're not sure. Next is pop. This method removes an item based on its index, and it also returns the item that was removed, which can be useful. Fruits equals kiwi, apple, blueberry, cherry, date. Use current list state. Removed item equals fruits. Pop 0, remove item at index 0. Print after popping index 0, fruits. Print item removed, removed item. Fruits.pop0 removed kiwi, which was at index 0, and we stored that removed value in the removed item variable. Last item equals fruits.pop, pop the last item if no index is given. Print after popping the last item, fruits. Print last item removed, last item. If you use pop without specifying an index, it removes and returns the last item in the list. This is a very common pattern when you're processing items from the end of a list. This will cause an error. Print trying to pop index 10 will cause error. Fruits.pop10. Just like with accessing, trying to pop an index that doesn't exist will give you an index error, pop index out of range. Another way to remove items is using the del keyword. Del is a Python statement, not a list method. You can use it to remove an item by index. Fruits equals apple, blueberry, cherry, use current list state. Del fruits 1, delete item at index 1. Print after deleting index 1, fruits. Del fruits 1 removed the item at index 1, which was blueberry. Unlike pop, del doesn't return the removed value. You can also use del with slices. MyList equals 1, 2, 3, 4, 5, 6. Del MyList 1:4. Delete items from index 1 up to, not including 4. Print after deleting slice 1 to 4, MyList. A cool feature of del is that you can also use it with slices to remove a range of items. Finally, if you just want to remove all items from a list and make it empty, you can use the clear method. Fruits equals apple, cherry, use current list state. Fruits.clear, remove all items. Print, after clearing the list, fruits. Clear empties the list, turning it into empty square brackets. It's quicker than removing items one by one if you want to start fresh with an empty list variable. Wow, we covered a lot of ways to change lists. We learned that because lists are mutable, you can change their contents. You now know how to change an item using its index, add items using append and insert, and remove items using remove, pop, and the del keyword, plus how to empty a list with clear. We also saw how to handle value error with remove and index error with pop. In part 3 of this series, we'll explore even more useful list methods like sorting, reversing, finding items, counting them, and very importantly, understanding how to make proper copies of lists to avoid tricky bugs. Ever seen your Python list change unexpectedly? The most common way beginners try to copy a list is actually a hidden trap that can silently corrupt your data. Lists have even more powerful tools. Today, we'll explore sorting, reversing, finding information, and crucially, proper list copying to avoid tricky mistakes. Let's head back to the code editor. We've seen how to add and remove. What about organizing the items? Python lists have methods to sort and reverse the list in place. Numbers equals 3, 1, 4, 1, 5, 9, 2. Print original numbers list, numbers. Numbers.sort, sort the list in ascending order. Print after sorting, numbers. The sort method arranges the items in ascending order by default. For numbers, it's from smallest to largest. For strings, it's alphabetical. Fruits equals cherry, banana, apple. Print original fruits list, fruits. Fruits.sort. Print after sorting fruits. See, alphabetical for strings. What if you want to sort in descending order, largest to smallest, or reverse alphabetical? You can pass an argument reverse equals true to the sort method. Numbers equals 3, 1, 4, 1, 5, 9, 2. Numbers.sort reverse equals true, sort in descending order. Print after sorting descending numbers. It's important to note that sort changes the list in place. It doesn't create a new list. Another useful method is reverse. This simply reverses the current order of the list regardless of the values. My list equals 1, 2, 3, 4, 5. Print original list, my list. My list.reverse, reverse the list in place. Print after reversing my list. Like sort, reverse also modifies the list in place. How do you find the index of a specific item? Use the index method. Fruits equals apple, banana, cherry, banana. Index of banana equals fruits.index banana finds the index of the first banana. Print index of first banana, index of banana. Index returns the index of the first item that matches the value you provide. This will cause an error. Print, trying to find index of grape will cause error. Fruits.index grape. If the item is not found, index raises a value error similar to remove. You get item is not in list. Again, you might want to check with in first if you're unsure if an item exists. What if you want to know how many times an item appears in a list? The count method is perfect for this. Numbers equals 1, 1, 2, 3, 4, 5, 9, 1. Count of 1 equals numbers.count 1. Count of 10 equals numbers.count 10. Print count of 1, count of 1. Print count of 10, count of 10. Count simply returns the number of times the value appears. If it's not in the list at all, it returns 0. This is a very important concept and a common source of bugs for beginners. Let's say you have a list and you want to make a copy of it so you can modify the copy without changing the original. Original list equals 1, 2, 3. This looks like a copy, but it's not a true copy. Alias list equals original list. Print original, original list. Print aliased, aliased list. If you do alias list equals original list, you might think you've made a copy. But in Python, this doesn't copy the list's contents. It just makes aliased list point to the exact same list in memory as original list. This is called aliasing. What happens if we change an item using aliased list? Original list equals 1, 2, 3. Aliased list equals original list, alias. Aliased list 0 equals 99. Change item in aliased list. Print original after changing aliased original list. Print aliased after changing aliased aliased list. Both lists changed because they are the same list. This is usually not what you want if you intend to work on a separate copy. To make a true copy, you need to create a new list object with the same contents. There are a few ways to do this. We saw one in part 1, slicing. Original list equals 1, 2, 3. Method 1, slicing. Sliced copy equals original list : creates a new list containing all items. Print original list. Print sliced copy. Using the full slice creates a brand new list. Now, if we change the sliced copy 0 equals 99, change item in the copy. Print original after changing sliced copy, original list. Print sliced copy after changing sliced copy. Only the copy changed. The original list is untouched. This is the desired behavior for a copy. Two other common ways to make a copy are using the copy method or the list constructor. Original list equals 1, 2, 3. Method 2, using copy method. Method copy equals original list dot copy. Print method copy. Method 3, using list constructor. Constructor copy equals list original list. Print constructor copy. Both original list.copy and list original list create a new list object. These three methods, slicing, .copy, list, create what's called a shallow copy. For lists containing simple items like numbers or strings, a shallow copy is usually enough. What about deep copies? This is a bit more advanced, but briefly, if you have a list containing other mutable objects like lists inside it, a list of lists, a shallow copy only copies the references to the inner lists, not the inner lists themselves. So changing an inner list in a shallow copy will affect the original. A deep copy from the copy module copies everything, including the inner lists. Most of the time you'll use shallow copies, but keep deep copy in mind for lists of lists. Another common mistake, which often comes up when you start looping through lists, which we'll do in a future video, is trying to add or remove items from a list while you are looping directly over that same list. Example of potential issue. Do not do this usually. My numbers equals 1, 2, 3, 4. For number in my numbers, if number modulo 2 equals 0, my numbers dot remove number, modifying the list we are looping over. Print my numbers can get unexpected results or skip items. Modifying a list while you are iterating over it using a standard for loop can lead to skipped items or unexpected behavior because you're changing the size and indices of the list as you go. A common way to avoid this is to iterate over a copy of the list instead, or create a new list with the items you want to keep. We'll see examples of this when we combine loops and lists later. Great job! We've added more tools to our list management toolbox. You learned how to sort and reverse lists, find the position of items with index, count items with count, and critically, how to make proper copies of lists to avoid unexpected changes due to aliasing. We also briefly touched on common mistakes like modifying while iterating and the difference between shallow and deep copies. We've covered the fundamentals and key operations. Now it's time to put this knowledge to work. In part 4, the final video in this series, we're going to build a simple to-do list manager project using everything we've learned about lists. You get to see how these pieces fit together in a real application. We're putting everything together to build a simple but functional command line to-do list manager application using just Python lists. We'll also look at a challenge to extend the project, hint at some advanced list ideas, and finally, I'll show you where to find all the bonus resources, including the challenge, quiz, and the code snippets. Let's code. Our goal is a simple program that lets us view our to-do list, add tasks, and mark tasks as done by removing them. Initialize an empty list to store our tasks. To-do list equals square brackets. Welcome message. Print welcome to the to-do list manager. First, we need a place to store our to-do items. A list is perfect. We'll start with an empty list called to-do list. We want the program to keep running until the user decides to exit. A while loop is great for this. We'll set a condition that's always true and break out of the loop when needed. Main loop to keep the program running. While true, print choose an option. Print 1, view to-do list. Print 2, add task. Print 3, mark task as done, remove. Print 4, exit. Get user input. Choice equals input. Enter your choice 1 to 4. Inside the loop, we'll print out the options the user has. Then we use input to get their choice. Now we need to handle each choice using if, elif, and else statements. Handle choices. If choice equals 1, print your to-do list. Check if the list is empty. If not to-do list, same as len to-do list equals 0. Print your list is empty. Else, loop through the list to display tasks with their number. For index task in enumerate, to-do list using enumerate is handy here. Print f index plus 1 task, displaying one based index to user. Print some dashes. If the choice is 1, we want to show the list. We first check if the list is empty using if not to-do list. This is a neat Pythonic way to say if the list is empty. If it is, we print a message. Otherwise, we loop through the tasks. Here, we use enumerate, which gives us both the index and the item as we loop. We print index plus 1 so the user sees a list starting from 1, which is more natural than starting from 0. Elif choice equals 2, task equals input, enter the task to add. To-do list.append task, use append to add to the end. Print f task added. If the choice is 2, the user wants to add a task. We get the task description using input. Then we simply use to-do list.append task to add the new task to the end of our list. Remember append from part 2? Super useful here. Elif choice equals 3. First, check if there are tasks to remove. If not, to-do list, print no tasks to mark as done. Continue, go back to the start of the while loop. Print your to-do list, select to remove. For index, task in enumerate, to-do list, printf index plus 1, task. Print some dashes. Get task number from user. They see one base numbers. Task number s star equals input. Enter the number of the task to mark as done. Error handling. Check if input is a number. If not, task number star dot is digit. Print invalid input. Please enter a number. Continue. Go back to the start of the while loop. Convert input to index. Remember lists are 0 indexed. Task index equals int. Task number star minus 1. Convert user's 1 base number to 0 based index. Error handling. Check if index is valid. If 0 less than or equals task index less than len to-do list, check if the index is within the valid range. Remove task equals to-do list.pop task index. Use pop to remove by index and get the task. Print f task remove task marked as done. Else, handle invalid task number. Print invalid task number. Please enter a number from the list. Choice 3 is a bit more involved. The user wants to remove a task. First, we check if the list is empty. You can't remove from an empty list. If not empty, we show the list again so the user can see the numbers. We ask for the number of the task they want to mark as done. Here's where error handling is important. What if the user types hello instead of a number? The isDigit string method helps us check if the input consists only of digits. If not, we print an error and continue the loop to show the menu again. If it is a number, we convert it to an integer using int. Crucially, the user sees numbers starting from 1, but lists use 0-based indexing. So if they enter 1, we need index 0. If they enter 3, we need index 2. We subtract 1 from their input. Task index equals int task number star minus 1. Next, we need to handle if they enter a number that's out of the valid range of indices. We check if task index is greater than or equal to 0 and less than the length of the list using 0 less than or equals task index less than len to-do list. This is a compact way to check if the index is valid. If the index is valid, we use todolist.popTaskIndex to remove the item at that index. Remember pop from part 2? It removes the item and gives it back to us, so we can print a nice message confirming which task was marked done. If the index is not valid, we print an invalid number message. elif choice equals 4. Print exiting to-do list manager. Goodbye. Break. Exit the while loop. If the choice is 4, the user wants to exit, we print a goodbye message and use the break keyword to exit the while loop. Else, handle invalid choices. Print invalid choice. Please enter a number between 1 and 4. Finally, if the user enters anything other than 1, 2, 3, or 4, the else block catches it and we print an invalid choice message. Then the loop continues showing the menu again. And that's our simple to-do list manager. We used an empty list, append to add, pop to remove by index, len to check if it's empty, and basic indexing and looping to display items. We also added some essential error handling for user input. Let's run it and see it in action. See how Python lists power a simple to-do app. Add tasks instantly. See your list update in real time. Mark tasks done with a single command. Simple, efficient, all built with Python lists. Okay, you've built the basic to-do list manager. Here's a challenge for you to extend it and practice your list skills even further. Add a new option, maybe number 4, called Edit Task. When the user chooses this, ask them which task number they want to edit. Remember to handle the one-based input. Then ask them for the new description of the task. You'll use the index you calculated and simple assignment to-do list index equals new description to update the item in the list. And don't forget the error handling we just learned for invalid task numbers. If you want to go even further, look into the extend method. How is it different from append when adding multiple items? Explore list comprehensions, which are a super Pythonic way to create lists based on existing ones. And check out nested lists. Lists that contain other lists, perfect for things like grids in games or matrices in data. These are fantastic next steps after mastering the basics we covered. Amazing work. You've successfully built your first application using Python lists and applied many of the concepts we learned throughout this series. You're going to master Python tuples, learning how to create them, access their data, and understand why they are a powerful, unchanging tool in your coding arsenal. Ever needed to store a collection of data that shouldn't accidentally change? Imagine storing exact geographical coordinates for a map, specific RGB color values for a design, or even a user's immutable profile details like their ID and date of birth. If you want to keep that data fixed and safe, Python's unsung hero, the tuple, is exactly what you need. So what exactly is a tuple? Think of a tuple as a list's cousin, but with a very important difference. Tuples are ordered and immutable. Ordered means the items are stored in a specific sequence, just like in a list. You can access them by their position, also known as their index, but immutable is the key. Once you create a tuple, you can't change, add, or remove its elements. It's fixed, permanent data. This makes them super reliable for data that should never be altered. Creating tuples is straightforward. The most common way is by using parentheses and separating items with commas. Theory: create 1. My tuple equals 1, 2, apple, true. Print my tuple. As you can see, my tuple holds numbers, a string, and a Boolean. Tuples can hold items of different data types, just like lists. Interestingly, you can sometimes create tuples without parentheses, especially when packing values. This is called tuple packing. Theory: create 2. Another tuple equals 10, 20, hello. Print another tuple. Python automatically understands that 10, 20, hello should be a tuple. A crucial point: if you want a tuple with just one item, you must include a comma after the item. Without it, Python treats it as a regular variable inside parentheses. Theory: create 3. Single item tuple equals 5. This is a tuple, not a tuple equals 5. This is just an integer 5 in parentheses. print type single item tuple, print type not a tuple. Notice the output. The one with the comma is a tuple, the other is an int. Don't forget that comma for single item tuples. And finally, an empty tuple is just empty parentheses. Theory. Create for empty tuple equals empty parentheses. Print empty tuple. Accessing elements in a tuple is exactly like accessing elements in a list or a string. You use indexing and slicing. Indexing starts from 0 for the first element. Theory access 1. Colors equals red, green, blue, yellow. Print colors 0, first element. Print colors 2, third element. Print colors -1, last element, using negative indexing. You can also grab a range of items using slicing. Remember, slicing start-end goes up to, but not including, the end index. Theory access 2, numbers equals 10, 20, 30, 40, 50, 60. Print numbers 1:4, elements from index 1 up to, but not including, 4. Print numbers 3, elements from start up to, not including, 3. Print numbers 3, elements from index 3 to the end. Tuples support many familiar operations. You can concatenate them, which means joining 2 or more tuples together to form a new tuple. Theory ops 1, tuple 1 equals 1, 2, tuple 2 equals A, B, combined tuple equals tuple 1 plus tuple 2. Print combined tuple. You can also repeat a tuple by multiplying it by an integer. Theory ops 2, my pattern equals x times 3. Print my pattern. Getting the length is simple with the len function. Theory ops 3, data equals 10, 20, 30. Print len data. And you can check if an item is in a tuple using the in operator. Theory ops 4, fruits equals apple, banana, cherry. Print banana in fruits. Print grape in fruits. For tuples containing only numbers, you can easily find the min, max, and sum. Theory ops 5, numbers equals 5, 1, 9, 3. Print min numbers, print max numbers, print sum numbers. This is the most crucial part about tuples, immutability. It means you cannot change elements after the tuple is created. Let me show you what happens if you try. Theory error 1. Coordinates equals 10, 20, 30. Let's try to change the first element. Coordinates 0 equals 5. This will cause an error. Print coordinates. And boom, you get a type error, tuple object does not support item assignment. This is Python telling you, hey, you can't change this tuple. This error is a feature, not a bug. It protects your data from accidental changes. If you need to change the data, you should probably use a list or convert the tuple to a list, make your changes, and then convert it back to a tuple if necessary. So with all this talk about mutability, when should you choose a tuple over a list? Use tuples when you have a collection of items that should not change. Think of fixed coordinates, database records where fields are static, or credentials. You want to use the collection as a dictionary key. Lists cannot be dictionary keys because they are mutable, but tuples can be. You're dealing with heterogeneous data, different types of data that logically belongs together, like a person's name and age, where the combination itself is fixed. You need to return multiple values from a function. Functions often return tuples by default if you return multiple items. Use lists when you need a collection of items that will change frequently, add, remove, modify elements. The order matters, but the items themselves are mutable. This marks the end of our first lesson on tuples. In the next video, we'll dive into hands-on coding, explore tuple packing and unpacking, and apply what we've learned to a practical project. In our previous lesson, we grasped the basics of tuples, their immutability, and how to create them. Now it's time to put that knowledge into action. We'll dive deeper into hands-on coding, explore powerful tuple packing and unpacking techniques, and build a practical project that showcases tuples in a real-world scenario. Plus, a challenging exercise and a peek into advanced tuple features await you. Let's code. First, let's create a few different types of tuples. Hands-on 1. Tuple of numbers. Numbers tuple equals 10, 20, 30, 40, 50. Print numbers tuple, tuple of strings. Fruits tuple equals apple, banana, cherry, date. Print fruits tuple. Time to try out the len, min, max, and sum functions. Other operations. Printf length of numbers, len numbers tuple. Print minimum number, min numbers tuple. Print maximum number, max numbers tuple. Print sum of numbers, sum numbers tuple. How to update a tuple by creating a new one. Person info equals Alice, 30, New York, true. Person info list equals list person info. Person info list 1 equals 31, change age in the list. New person info equals tuple person info list. Print new person info, updated age, new person info. This shows that while tuples themselves are immutable, you can always derive new tuples from existing ones. One of the most elegant features of tuples is packing and unpacking. This allows you to assign multiple values to multiple variables in a single clean line. Hands-on 2. Tuple packing. Coordinates equals 10, 5, 20, 3. This is implicitly packing into a tuple. Print coordinates packed, coordinates, tuple unpacking. XY equals coordinates, unpacking the coordinates tuple. Print unpacked x, x, unpacked y, y. Another example, swapping variables. A equals 5, B equals 10. Print before swap A equals A, B equals B. A, B equals B, a Pythonic way to swap using packing, unpacking. Print after swap A equals A, B equals B. Unpacking with function returns. Def get user data. Name equals Bob. Age equals 25. City equals London. Return name, age, city. Function returns a tuple, packed. Username, user age, user city equals get user data. Unpacking the return tuple. Print user data, name equals username, age equals user age, city equals user city. As you can see, tuple packing and unpacking make your code much more readable and concise, especially for variable swaps or when functions need to return multiple values. Like lists, you can easily loop through the elements of a tuple using a for loop, iterating through a tuple. Print iterating through fruits tuple. For fruit and fruits tuple, print fruit, iterating with index. Print iterating through person info with index. For index, item and enumerate person info. Print f index index item. This makes processing tuple elements very straightforward. Let's apply what we've learned to a practical project. We'll create a simple coordinate tracker where we store a list of geographical points. Using tuples for each point ensures that once a coordinate is recorded, its latitude and longitude don't accidentally change. A list to store our immutable coordinate points. Each point will be a tuple latitude, longitude. Tracked points equals square brackets. Function to add a new point. Def add point, lat lon. New point equals lat lon. Create a tuple for the point. Tracked points dot append new point. Print added point, new point. Function to display all tracked points. Def display points. Print tracked points. If not tracked points, print no points tracked yet. Else for I, point in enumerate tracked points. Unpack the tuple for clear output. Latitude longitude equals point. Print point I plus 1, latitude equals latitude, longitude equals longitude. Print some dashes. Let's add some points. Add point 34.0522 minus 18.2437 Los Angeles. Add point 40.7128 minus 74.0060 New York. Add point 51.5074 0.1278 London. Display points. Display points. Try to modify a point will not work directly as tuples are immutable. Tracked points 0, 0 equals 35.0. This would cause an error. If we needed to update a point, we'd replace the entire tuple in the list. Print attempting to update a point by replacing it in the list. If tracked points, replace the first point with new coordinates. Tracked point 0 equals 34.0522 minus 188.24. Slightly change longitude. Print updated first point in list, track point 0. Display points. When we run this code, you'll see how we can add points, display them, and importantly, if we needed to change a coordinate, we'd have to replace the entire tuple in our list rather than changing a single element within it. This immutability ensures data integrity for each recorded point. Now it's your turn to put your tuple skills to the test. Challenge. You're given a list of student records, where each record is a tuple containing student ID, name, grade. Your task is to write a Python script that 1. Finds and prints the name of the student with student ID equals 103. 2. Counts how many students have a grade of A. 3. Bonus. Sorts the student records list by name, alphabetically. Hint. You might need to use the sorted function with a lambda to specify the sorting key. Pause the video, try it out, and then come back to see how you did. Welcome back. How did you do? If you got stuck, don't worry. Practice is key. For further exploration, I want to quickly introduce you to something called a named tuple from Python's collections module. If you're dealing with tuples where the meaning of each element isn't immediately clear, like 10, 20 could be x, y, or lat lon, named tuple lets you give names to tuple positions, making your code much more readable. From collections, import named tuple. Define a named tuple for a point. Point equals named tuple, point x, y. Create a point using named tuple. P1 equals point, x equals 10, y equals 20. P2 equals point, 30, 40. You can still use positional arguments. Print point 1 P1. Print accessing x with name P1x. Print accessing y with index P11. Still works like a regular tuple. See how much clearer P1.x is than P10? It's a great way to make your immutable data self-documenting. Another powerful use case for tuples is as dictionary keys. Remember how we said tuples are immutable? Well, dictionary keys must be immutable, so while you can't use a list as a dictionary key, you can absolutely use a tuple. This is great for composite keys, like mapping city zip code to data. using tuples as dictionary keys. Location data equals London SG1A 0AA, Buckingham Palace, Paris 7501, Louvre Museum, 34 0522 18 2437, Los Angeles, using coordinates as key. Print London landmark, location London SW1A 0AA, print LA landmark, location data 34 0522 -1 through 7. This opens up very flexible ways to structure your data. Wow, we've covered a lot about tuples. Key takeaways. Tuples are Python's immutable ordered sequences, perfect for data that should not change. Versatile creation and access. You can create them with or without parentheses, packing, and access elements using indexing and slicing. Powerful unpacking makes your code cleaner, especially for variable swaps or multi-value function returns. Practical applications. Ideal for storing fixed records like coordinates, RGB values, or composite dictionary keys. Ever wonder how to store data that's not just a list of items, but more like a real-world dictionary where you look up words to find their meanings? Python dictionaries are exactly that, powerful tools for storing information in key value pairs. We'll unlock the secrets of dictionaries, from creating them to performing all sorts of operations that will make your code more organized and efficient. Get ready to level up your data handling skills. By the end of this video, you'll be a pro at handling key value data in Python. So, what exactly is a dictionary in Python? Imagine your phone book. Each name has a phone number, right? You look up a name, that's your key, to find the phone number, that's your value. A Python dictionary works in the exact same way. It stores data in key value pairs. Each key is unique, just like you wouldn't have two identical names in your phone book pointing to different numbers, and each key is connected to a specific value. My phone book equals Alice 1234567, Bob 9876543, Charlie 5551212. How do they differ from lists? Well, lists are ordered and you access items using their position, like my list 0. Dictionaries, however, are unordered, and you access items using their unique keys, not numbers. This makes them perfect for representing real-world objects or settings, like a student's profile or configuration settings for a program. My list equals apple, banana, cherry. Print my list 0. Output apple. My fruit prices equals apple 10, banana 0.5, cherry 2. Print my fruit price is apple, output 1.0. Creating dictionaries is super easy. The most common way is using curly braces. Creating an empty dictionary. Empty dict equals curly braces. Print empty dict. You can also create a dictionary with some initial data. Just list your key value pairs inside the curly braces, separating them with commas. Each pair has a key, then a colon, then its value. Creating a dictionary with initial data. Student equals name Alice, age 20, major computer science, print student. Another way is using the dict constructor. You can pass a list of key value tuples or keyword arguments to it, using dict constructor. Another dict equals dict, brand equals Ford, model equals Mustang, year equals 1964. Print another dict, or from a list of tuples. Tuple dict equals dict, color, red, size, large. Print tuple dict. Once you have a dictionary, how do you get a specific value out of it? You use the key, just like you would look up a word in a real dictionary. Student equals name Alice, age 20, major computer science. Print student name, output Alice, print student age, output 20. But be careful, if you try to access a key that doesn't exist, Python will raise a key error. This is a common mistake. This will cause a key error. Print student gender. To avoid this, you can use the get method. This method lets you provide a default value to return if the key isn't found instead of crashing your program. It's much safer. Using .get for safer access. Print student.get major, output computer science. Print student.get gender, NA, output NA, default value. Print student.get grade, output none, default if not specified. Dictionaries are dynamic, meaning you can easily add new key value pairs, update existing values, and even delete pairs. Student equals name, Alice, age 20, major, computer science, adding a new key value pair. Student city equals New York. Print student. To update an existing value, you simply assign a new value to an existing key. Updating an existing value. Student age equals 21, print student. And if you want to remove a key value pair, you can use the del keyword. Deleting a key value pair. Del student city, print student. There are a few handy operations you can perform on dictionaries. First, len tells you how many key value pairs are in your dictionary. Student equals name, Alice, age, 21, major, computer science, print, len, student, output, 3. The in keyword is great for checking if a key exists in your dictionary. It returns true or false. Print, name and student, output, true. Print gender and student, output false. You can also easily loop through dictionaries. Keys gives you all the keys, values gives you all the values, and items gives you both as key value pairs. Looping through keys, print keys for key and student keys, print key, looping through values, print values for value and student values, print value, looping through items, key value pairs, print items for key value and student items, print key value. All right, let's get our hands dirty with some live coding. We're going to build a simple student record dictionary. This is a common real-world scenario where dictionaries shine. First, let's create an empty dictionary to hold our students' details. Create an empty student dictionary. Student record equals curly braces. Print empty student record, student record. Now, let's add some details. We'll include name, age, grade, and subjects. Remember, keys are usually strings, and values can be any data type, even a list. Add student details. Student record name equals John Doe. Student record age equals 17. Student record grade equals 11th. Student record subjects equals math, science, history. Print. After adding details, student record. How about accessing a specific detail? Like the student's age? Easy, just use the key. Access and print specific details. Print student's age, student record, age. What if John's grade improves? We can easily update an existing value. Update a student's grade. Student record grade equals 12th. Print, after grade, update, student record. And let's say John decides to take an art class. We can add a new subject to his list of subjects. Add a new subject. Student record subjects append art. Print after adding a new subject, student record. Before trying to access something that might not be there, it's good practice to check if a key exists using the in keyword. For example, if we wanted to know their gender, but it's not always in the record, demonstrate checking if a key exists. If gender in student record, print student's gender, student record, gender. Else, print gender information not available. Using get is even cleaner. Gender equals student record, get gender not specified. Print student's gender using get gender. Finally, let's see how we can iterate through all the student's details, printing both the key and its value. This is super useful for displaying all the information. Show iterating through all student details. Print all student details for key, value, and student record. Items, print key, value. As you start working with dictionaries, you might run into a few common pitfalls. Let's look at them and how to fix them. Mistake 1, forgetting quotes around keys. Dictionary keys are almost always strings, so you need to put them in quotes. If you forget, Python will think it's a variable name. Common mistake, forgetting quotes. My dict equals name Alice. This will cause an error if name is not defined. Solution, always use quotes for string keys. My dict equals name Alice, print my dict. Mistake 2, trying to access a non-existent key without get. We talked about this. It leads to a key error, which stops your program. Common mistake, accessing a non-existent key. Print student record email. This will cause key error. Solution, use .get or check with in keyword. Email equals student record, get email, email not provided. Print email. Mistake 3, trying to use list indexing on dictionaries. Remember, dictionaries don't use numerical positions like lists. You must use keys. Common mistake, using list indexing, print student record 0. This will cause a key error. Solution, use keys to access values. Print student record name. Wow, you've just taken a huge step in mastering Python data structures. In this first part, we've unlocked the fundamental concepts of Python dictionaries. Dictionaries are even more powerful than you think. In this second part, we're going to dive into some more advanced tricks, including how to sort dictionary data, and then we'll put all that knowledge into action by building a practical, simple inventory management system. All right, let's jump straight into our mini project, a simple inventory management system. This is a fantastic way to see how dictionaries can organize complex data efficiently. Our goal is to use a dictionary to store product inventory. The product name will be our key, and the value will actually be another dictionary containing the product's quantity and price. This is called a nested dictionary, a dictionary inside another dictionary. Let's start by initializing our empty inventory dictionary. Initialize an inventory dictionary. Inventory equals curly braces. Print initial inventory, inventory. Now, let's add some products with their quantities and prices. Notice how the value for each product key is another dictionary. Add new products. Inventory laptop equals quantity 10, price 1200. Inventory mouse quantity 50, price 25. Inventory keyboard equals quantity 30, price 75. Print inventory after adding products. A better print for readability. For product details in inventory, items, print F, product, quantity equals quantity, price equals details, price, :2F. Imagine a sale happens and we sell 2 laptops. We need to update the quantity of the laptop product. We access the laptop key, then inside that dictionary, we access the quantity key. Update the quantity of an existing product. If laptop in inventory, good practice, check if product exists. Inventory laptop quantity minus equals 2. Print sold 2 laptops, new quantity, inventory laptop quantity. Else, print laptop not found in inventory. What if a new shipment of mice arrives? We'll update the quantity again, this time increasing it. Add more quantity for a product. If mouse in inventory, inventory mouse quantity plus equals 10, print received 10 mouse units. New quantity, inventory, mouse, quantity, else, print mouse not found in inventory. Now let's calculate the total value of a specific product, say keyboard. This involves getting both its quantity and price. Calculate total value of a specific product. Product name equals keyboard. If product name in inventory, QD equals inventory product name, quantity, price equals inventory product name, price. Total value equals QD times price. Print total value of product name, total value : dot 2F. Else, print product name not found in inventory. Finally, let's display our entire inventory in a nice readable format. We'll loop through the main inventory dictionary and then access the nested quantity and price. Display the entire inventory. Print current inventory. If not inventory, print inventory is empty. Else, for product details in inventory.items, print product, print quantity, details quantity, print price, details price, : dot 2F, format price to 2 decimal places. Print dash times 20, separator for readability. Beyond what we've already covered, Python dictionaries have even more useful methods, and we'll also look at how to sort dictionary data. Pop key removes the item with the specified key and returns its value. Great for getting a value and removing it at the same time. Pop item removes and returns a random or last in Python 3.7+ key value pair. Clear removes all items from the dictionary, making it empty. Copy returns a shallow copy of the dictionary. Important because direct assignment just copies the reference, not the dictionary itself. Update other dict merges another dictionary or an iterable of key value pairs into the current dictionary. Existing keys will be updated, new keys will be added. My items equals apple 5, banana 10. Removed value equals my items. Pop apple, print pop apple, remove value, dict my items. My items clear, print after clear, my items. Original equals A1, B2, copied equals original, copy. Copied A equals 100, print original after copy change, original. Print copied. Dict1 equals name Alice, age 30. Dict2 equals age 31, city, New York. Dict1 to update Dict2, print after update, Dict1. Now let's talk about sorting dictionaries. Remember, dictionaries are inherently unordered, but you can get a sorted list of their keys, values, or even items using the built-in sorted function. This is super useful for presenting data in a specific order. Sorting dictionaries. Scores equals math 90, science 85, art 95, English 88. Print original scores dictionary, scores. Sorting by keys, alphabetical order by default. Sorted keys equals sorted, scores, keys. Print sorted keys, sorted keys. You can then iterate using the sorted keys. Print scores sorted by key. For key and sorted keys, print key, scores key. You can also sort by values. This requires a bit more advanced usage of sorted with a key argument, but it's very powerful. We'll sort by value from lowest to highest. Sorting by values. Using a lambda function to tell sorted to use the second element of each item, which is the value for sorting. Sorted items by value equals sorted, scores items, key equals lambda item, item 1. Print scores sorted by value ascending. For key value and sorted items by value, print key value, To sort in descending order of value, sorted items by value desk equals sorted, scores. Items, key equals lambda item, item 1, reverse equals true. Print, scores sorted by value descending. For key, value, and sorted items by value desk, print, key, value. Notice that sorted returns a list of tuples for items or just values for keys values. It doesn't change the original dictionary's order because dictionaries themselves don't have a fixed order in older Python versions, though newer versions, 3.7 plus, maintain insertion order. Regardless, sorted gives you a beautiful ordered list of your data. Now it's your turn to put your dictionary skills to the ultimate test. Your challenge is to create a word frequency counter. Given a sentence, your task is to count how many times each word appears and store these counts in a dictionary. The words should be the keys and their counts should be the values. Example, input sentence, Python is fun and Python is powerful. Expected output, order of words may vary, but counts should be correct. Python, 2, is 2, fun 1, and 1, powerful 1. Bonus challenge, after counting, print the words and their frequencies sorted alphabetically by word. Here are some hints to get you started. 1. How can you split the sentence into individual words? Hint, think about string methods. 2. How will you handle capitalization and punctuation? Hint, make all words lowercase and remove unwanted characters. 3. For each word, how will you check if it's already in your frequency dictionary and what should you do if it is or isn't? Hint, use in or get and increment the count. 4. For the bonus challenge, how can you use the sorted function on the dictionary's keys? Try this challenge on your own. It's a fantastic way to solidify your understanding of dictionaries. Wow, you've just mastered Python dictionaries. We've seen how they provide a flexible way to store and retrieve data using key-value pairs, making your code more intuitive and powerful. Remember, dictionaries are incredibly versatile and will be invaluable in your Python journey. What's next on our Python journey? We'll dive into another powerful data structure, sets and set operations. Get ready to learn about unique collections and powerful ways to combine or compare them. Have you ever found yourself needing to handle unique items in your data or wished you could perform mathematical operations like unions and intersections directly in your code? Well, get ready to unlock the power of Python's set data structure. We're going to dive into what sets are, how to create them, and all the fundamental operations you can perform. By the end of this lesson, you'll be able to efficiently manage unique data and solve common programming challenges with ease. Let's get started. So what exactly is a Python set? Think of a set as a special kind of collection, like a list, but with a super important rule. Every item inside a set must be unique. That's right, no duplicates allowed. If you try to add an item that's already there, the set simply ignores it. Another key thing to remember is that sets are unordered. This means the items don't have a specific position or index, unlike lists or strings. This uniqueness and unordered nature makes sets incredibly powerful for certain tasks, especially when you need to quickly check for membership or remove duplicates from your data. Now that we know what sets are, let's see how to create them. There are a couple of common ways. The most straightforward is using curly braces, just like dictionaries, but without key-value pairs. Creating an empty set. My empty set equals set. Print empty set, my empty set. Creating a set with elements. Fruits, apple, banana, cherry. Print fruits set fruits. Notice how we used set for an empty set. If you just use curly braces by itself, Python thinks you're creating an empty dictionary, not a set. So for an empty set, set is your friend. You can also create a set from other iterable objects like lists or strings using the set constructor. This is super useful for getting unique items from existing data. Creating a set from a list. Numbers list equals 1, 2, 2, 3, 4, 4, 5. Unique numbers equals set numbers list. Print unique numbers from list, unique numbers. Creating a set from a string, unique characters. Text equals hello world. Unique chars equals set text. Print unique characters from string, unique chars. See how Python automatically removes the duplicates when converting from a list or string? That's the power of sets in action. One important point to remember is that while the set itself is mutable, meaning you can add or remove elements, the individual elements within a set must be immutable. This means you can store numbers, strings, or tuples, but not lists or dictionaries directly inside a set. If you try to add a mutable object, you'll get an error. This will cause an error. My set equals 1, 2, 3. Print my set. If you uncomment that line and run it, you'd get a type error because a list is a mutable type. Just keep that in mind when choosing what to put in your sets. All right, let's talk about the basic things you can do with sets. First up, checking if an item is in a set. This is super fast and efficient with sets thanks to their internal structure. We use the in operator just like with lists or strings. My set equals apple, banana, cherry. Print apple in my set, apple in my set. Print grape in my set, grape in my set. Next, adding elements. We use the add method to add a single item. If the item already exists, add simply does nothing. No error, no duplicate. My set, add orange. Print, after adding orange, my set. My set, add apple, adding an existing element. Print, after adding apple, again, no change. What if you want to add multiple elements at once? That's where update comes in handy. You can pass it any iterable, like a list or another set, and it will add all the unique items. My set, update, grape, kiwi, banana. Print, after updating with a list, my set. Now, let's look at removing elements. There are two main methods, remove and discard. Both do pretty much the same thing, but there's a crucial difference you need to know. My set, remove kiwi. Print, after removing kiwi, my set. My set, remove mango. Uncommenting this line will raise an error. Print, after trying to remove mango, my set. If you try to remove an element that isn't in the set using remove, Python will give you a key error. This is often what you want if you expect the item to be there and want to know if it's missing. But sometimes you just want to make sure an item isn't in the set and you don't care if it was there in the first place. That's when discard is perfect. My set, discard, orange. Print, after discarding orange, my set. My set, discard, mango, discarding a non-existent element. Print, after trying to discard mango, my set. No error, no change. See, discard just silently does nothing if the item isn't found. Choose remove when you expect the element to be there and want an error if it's not. Choose discard when you don't mind if the element is missing. Finally, we have pop. This method removes and returns an arbitrary element from the set. Remember, sets are unordered, so you can't predict which element pop will remove. It's useful if you just need to get any element out of the set. Popped element equals my set.pop, print popped element, print set after pop, my set. If you call pop on an empty set, you'll get a key error. To really cement the difference between sets and other collections like lists, let's look at this simple diagram. Imagine you have a list with items A, B, A, C. As you can see, a list holds onto every item, including duplicates, and keeps them in a specific order. Now, if you take those same items and put them into a set, something magical happens. The set automatically identifies and removes the duplicate A, leaving you with only the unique elements, A, B, C. And notice they are no longer in a specific order. This visual really highlights why sets are your go-to for ensuring uniqueness and for fast membership checks. All right, let's get our hands dirty with some live coding. A very common task in programming is dealing with duplicate data. Imagine you have a list of user IDs from a survey, and some users might have accidentally submitted multiple responses. You need to find out how many unique users participated. Sets are perfect for this. Getting unique items from a list. Survey responses equals user A, user B, user A, user C, user D, user B. Print original survey responses with duplicates. Survey responses. Unique users equals set survey responses. Print unique users from survey, unique users. Print number of unique users, len unique users. Look how simple that was. Just by converting our survey responses list to a set, all the duplicates are gone, and we instantly get our list of unique users. Then we can use len to count them. This is far more efficient than writing a complex loop check for duplicates manually. Now, let's simulate building a set based on some operations, perhaps from a game inventory or a list of enrolled students. We'll start with an empty set and then add and remove items, observing how the set behaves. Building a set interactively. Game inventory equals set. Print initial inventory, game inventory. Add items. Game inventory dot add sword. Print after adding sword, game inventory. Game inventory dot add shield. Print after adding shield, game inventory. Game inventory dot add sword. Try to add sword again. Print after trying to add sword again, game inventory. No change, still unique. Game inventory dot update potion gold sword. Add multiple items. Print after updating with potion gold sword, game inventory. Remove items. Game inventory dot discard shield. Print after discarding shield, game inventory. Game inventory dot discard axe. Try to discard non-existent item. Print after trying to discard axe, game inventory, no error. What if we use remove for a non-existent item? Uncomment the line below to see the error. Game inventory dot remove key. Print after trying to remove key, game inventory. As you can see, when we tried to add sword a second time, the set simply ignored it. That's the unique nature of sets at work. And when we use discard for axe, which wasn't in our inventory, no error occurred, which can be very useful for robust code. If you uncommented that remove line, you would have seen a key error, just as we discussed. Remember, each lesson has related resources like code snippets, a challenge exercise, a quiz that will be assessed automatically right after submission, and will show the result and key takeaways available in the video description. Make sure to check them out. That wraps up the basics of Python sets. We've covered what they are, how to create them, and the fundamental operations. In this second and final lesson of our series, we're diving into the really powerful stuff, performing mathematical set operations like unions, intersections, and differences directly in your code. We'll also tackle a fun mini project to see how sets solve real-world problems. By the end of this video, you'll not only understand these advanced operations, but also know exactly when and how to use them. Let's pick up right where we left off. All right, let's jump straight into the core of advanced set usage, mathematical operations. Python sets beautifully implement concepts from set theory, allowing us to do things like combine sets, find common elements, or find elements unique to one set. We'll explore four main operations: union, intersection, difference, and symmetric difference. Let's set up two example sets, set A and set B, set operations. Set A equals 1, 2, 3, 4, 5. Set B equals 4, 5, 6, 7, 8. Print set A, print set B, set B. First up, union. The union of two sets contains all the unique elements from both sets. Think of it as combining everything without any duplicates. You can achieve this using the pipe operator or the union method. Union, all unique elements from both sets. Union set equals set A, union set B. Print union set A, set B, union set. Union method equals set A, union set B. Print F, union set A, union set B, union method. Next, intersection. The intersection of two sets contains only the elements that are common to both sets. These are the elements that appear in both set A and set B. We use the ampersand operator or the intersection method. Intersection, elements common to both sets. Intersection set equals set A ampersand set B. Print intersection set A ampersand set B intersection set. Intersection method equals set A intersection set B. Print intersection set A intersection set B intersection method. Moving on to difference. The difference set A minus set B contains all elements that are in set A, but not in set B. It's like asking, what does A have that B doesn't? We use the minus operator or the difference method. Difference, elements in set A, but not in set B. Difference AB equals set A minus set B. Print, difference set A minus set B, difference AB. Difference method equals set A difference set B. Print, difference set A difference set B, difference method. Important, the order matters for difference. Difference BA equals set B minus set A. Print difference set B minus set A, difference BA. Notice how the result changes if we do set B minus set A. The order absolutely matters for difference operations. Finally, symmetric difference. This one is really cool. The symmetric difference contains all elements that are in set A or set B, but not in both. Think of it as all unique elements that are not common. It's the opposite of intersection. We use the caret operator or the symmetric difference method. Symmetric difference, elements in either set but not in both. Symmetric difference set equals set A caret set B. Print symmetric difference set A caret set B, symmetric difference set. Symmetric difference method equals set A symmetric difference set B. Print symmetric difference set A symmetric difference set B, symmetric difference method. And there you have it. These four operations are incredibly powerful for data analysis and filtering. Now, a common mistake beginners make with sets is forgetting that sets are unordered. This means you cannot expect elements to be retrieved or printed in a specific order, even if you put them in that way. For example, common mistake, expecting order. My ordered items equals 5, 1, 3, 2, 4. Print set created from 5, 1, 3, 2, 4, my ordered items. Output might be 1, 2, 3, 4, 5, or 5, 1, 2, 4, or anything else. See how the output might not match the order you defined? If order is important for your use case, a list or tuple is a better choice. Sets are optimized for uniqueness and quick membership checks, not for maintaining order. Let's put these powerful set operations to work with a practical mini project. Imagine you're a website administrator and you've collected unique visitor IDs for your site over 2 different days. Your boss wants to know some key metrics: total unique visitors across both days, visitors who visited on both days, visitors who visited only on day 1, visitors who visited on only one of the days but not both. This is a perfect scenario for using sets. Let's define our visitor IDs as sets. Mini project, analyzing website visitors. Day 1 visitors equals Alice, Bob, Charlie, David, Eve. Day 2 visitors equals Charlie, Frank, Alice, Grace, Heidi. Print day 1 visitors, day 1 visitors. Print day 2 visitors, day 2 visitors. Print dash times 30. First, let's find the total unique visitors across both days. Which set operation should we use here? If you thought union, you're absolutely right. We want everyone who visits on either day. 1. Total unique visitors across both days, union. Total unique visitors equals day 1 visitors.union, day 2 visitors. Print total unique visitors, union, total unique visitors. Print count, len, total unique visitors. Print dash times 30. Great, now how about visitors who visited on both days? This means they are present in both day 1 visitors and day 2 visitors. This is a classic case for intersection. 2. Visitors who visited on both days, intersection. Visitors on both days equals day 1 visitors dot intersection day 2 visitors. Print visitors on both days, intersection visitors on both days. Print count len visitors on both days. Print dash times 30. Next, we want to find visitors who visited only on day 1. This means they were in day 1 visitors but not in day 2 visitors. This calls for a difference operation. 3. Visitors who visited only on day 1 difference. Only day 1 visitors equals day 1 visitors dot difference day 2 visitors. Print visitors who visited only on day 1 difference. Only day 1 visitors. Print count len only day 1 visitors. Print dash times 30. Finally, let's find visitors who visited on only one of the days but not both. This means they are unique to either day 1 or day 2 but not in the common group. This is the perfect job for symmetric difference. 4. Visitors who visited on only one of the days, symmetric difference. Only one day visitors equals day 1 visitors, symmetric difference, day 2 visitors. Print visitors who visited on only one of the days, symmetric difference, only one day visitors. Print count len only one day visitors. Print dash times 30. And there you have it. With just a few lines of code, using Python sets, we've extracted valuable insights from our visitor data. This mini project perfectly demonstrates how these set operations can simplify complex data analysis tasks. Imagine trying to do this with just lists and loops. It would be much more complicated and less efficient. Now it's your turn to put your set skills to the test. Here's a coding challenge for you. Given a list of strings, write a Python script that finds all the unique characters present across all strings and then identifies which characters appear in every single string. Example input, words equals hello world Python. Expected output, all unique characters, O, D, E, H, L, N, P, R, T, W, Y. Characters in every string, O. Pause the video here, give it a shot, and then come back to compare your solution. Remember, the goal is to use sets efficiently. Beyond what we've covered, sets have even more to offer. Here are a few ideas for further exploration. Frozen set for immutable sets. Sometimes you need a set that cannot be changed after it's created. This is where frozen set comes in. It's an immutable version of a set, which means you can even use a frozen set as an element inside another set or as a dictionary key, unlike regular sets. Frozen set example. Immutable set equals frozen set, 1, 2, 3. Immutable set dot add 4. This would raise an attribute error. Print frozen set, immutable set. It's read-only, making it useful in situations where you need a hashable set. Set theory in mathematics. Python sets are directly inspired by mathematical set theory. Concepts like union, intersection, and difference come straight from mathematics. Understanding the mathematical background can deepen your understanding of why these operations work so powerfully in programming. More advanced set methods. Python sets offer other useful methods you might want to explore. The subset checks if one set is a subset of another. All its elements are in the other set. The superset checks if one set is a superset of another, contains all elements of the other set. Is disjoint checks if two sets have no elements in common, their intersection is empty. Set x equals 1, 2. Set y equals 1, 2, 3, 4. Set z equals 5, 6. Print is set x a subset of set y? Set x is subset set y. Print is set y a superset of set x? Set y is superset set x. Print are set x and set z disjoint? Set x is disjoint set z. These methods provide even more tools for comparing and analyzing your unique data. Phew, we've covered a lot about Python sets in these 2 lessons. Let's quickly recap the key takeaways. Sets are unordered collections of unique elements. They are fantastic for ensuring uniqueness and for fast membership testing. You learned to create sets using curly braces or the set constructor. We covered basic operations like add, update, remove, discard, and pop, and how to use the in operator. And today we unlock the power of mathematical set operations. Union combines all unique elements from both sets. Intersection finds elements common to both sets. Difference finds elements in one set but not the other. Symmetric difference finds elements unique to each set, not in common. You also saw how sets can solve real-world problems like analyzing website visitor data. Ever found yourself writing the same lines of code over and over again? Or maybe your scripts are getting a bit messy and hard to follow. What if I told you there's a magical way to organize your code, make it reusable, and keep it super clean? Welcome to the exciting world of Python functions. We're diving deep into what functions are and how they work. We'll specifically focus on their super flexible companions, parameters, which let you feed information into your functions. By the end of this first part, you'll be writing modular, efficient, and truly professional Python code. Let's get started. All right, let's kick things off by understanding what functions actually are. Think of functions like mini programs or specialized tools in your coding toolbox. Imagine you have a specific task like calculating the area of a circle. Instead of writing the calculation steps every time you need it, you can package those steps into a single function. Then, whenever you need to calculate an area, you just call that function. Why should we use them? Well, there are three big reasons. First, reusability. This is all about the DRY principle that stands for don't repeat yourself. If you have code that you'll use multiple times, put it in a function. It saves you time and keeps your code neat. Second, readability. Functions help break down big problems into smaller, more manageable pieces. This makes your code much easier to understand, not just for you in the future, but for anyone else looking at it. And third, maintainability. When you need to fix a bug or add a new feature, you only have to change the code in one place, inside the function, instead of hunting down every instance of that repeated code. Super efficient. So how do we actually create a function in Python? We use the special keyword def. Def function name. This is the function body. Pass. You start with def, then give your function a name, choose something that describes what it does, followed by empty parentheses and a colon. Everything indented after the colon belongs to that function. Python uses indentation to know what's part of your function. If you forget to indent, Python will get confused. That pass keyword you see there, it's just a placeholder. It means do nothing for now. We use it when we want to define a function but haven't written its actual code yet. Let's look at a simple example. Here's a function that just prints hello world. Def say hello, print hello world. Now, defining a function is like writing a recipe. It doesn't actually do anything until you follow the recipe, right? The same goes for functions. To make our say hello function actually run, we have to call it. You just write the function's name followed by parentheses. Say hello, this calls the function. When we run this, you'll see hello world printed on the screen. Simple, right? Now, functions are great for repeating tasks, but what if you want your function to do something slightly different each time? This is where parameters come in. Think of parameters like the ingredients you give to a recipe. A cookie recipe always tells you how to make cookies, but you can change the ingredients, maybe add chocolate chips or nuts to get slightly different cookies. Parameters are those flexible inputs for your function. Def function name, param1, param2, function body uses param1 and param2. We define parameters inside the parentheses when we create our function. Each parameter acts like a special variable that will hold the value we give it when we call the function. Let's modify our greet function to take a name as a parameter. Def greet name, printf hello name. The name variable holds the passed value. Now, when we call greet, we'll pass in a name and the function will use it to create a personalized message. This makes our function much more flexible. All right, time to get our hands dirty with some live coding. Open up your Python editor and follow along. First, let's create a very basic function, much like our hello world example. We'll call this greet simple. Part 1, basic function creation. Def greet simple. Print, Welcome to our Python tutorial. Now, to make it run, we call it greetSimple. And there it is. Welcome to our Python tutorial. See? We can call it multiple times, and it does the same thing each time. That's reusability in action. greetSimple, greetSimple. A very common mistake for beginners is forgetting the parentheses when calling a function. Watch what happens if I type greetSimple without and try to run it. Print greetSimple. This is wrong. See? It doesn't print our message. Instead, it prints something like function greetSimple at some address. This tells us that greetSimple without parentheses refers to the function object itself, not the result of running the function. Always remember those parentheses to execute the function. Now let's make our greet function a bit smarter by adding a parameter. This is a positional parameter, meaning its position when you call the function matters. Part 2, introducing positional parameters. Def greet name, print hello name, nice to see you. Now, when we call it, we pass in a name inside the parentheses. Greet name Alice, greet name Bob. See how it customizes the greeting? Super cool. Another common mistake. What happens if I forget to give greet name a name when I call it? Greet name, this is wrong. Boom, type error, missing one required positional argument, name. Python is telling us, hey, I need a value for that name parameter. You must provide a value for every required parameter when you call a function. Functions can take multiple parameters too. Let's create a function to add numbers. Part 3, multiple positional parameters. Def add numbers, num1, num2, total equals num1 plus num2. Print, the sum of num1 and num2 is total. We call it by providing two numbers separated by a comma, add numbers 5, 3, add numbers 10, 20. For addition, the order add numbers 3, 5 gives the same result as add numbers 5, 3. But imagine if this was a subtract function. Subtract 10, 5 is 5, while subtract 5, 10 is negative 5. So for positional arguments, the order you pass them in absolutely matters. Keep that in mind. And that brings us to the end of part 1. We've covered the basics of defining and calling functions and how to use positional parameters to make your functions flexible. I hope you're already seeing the power of functions in making your code cleaner and more efficient. In part 2, we'll dive deeper into more advanced parameter types like default parameters and keyword arguments. Plus, we'll build a fun project. In part 1, we learned the basics of functions and how to use positional parameters. We're taking our function game to the next level. We'll dive into default parameters, which let you make some inputs optional, and keyword arguments, which give you incredible flexibility when calling your functions. Plus, we'll put everything together to build a practical calculator project. Get ready to supercharge your Python skills. Let's jump in. All right, let's start with default parameters. Sometimes you want a function to have a common behavior, but also allow for customization when needed. This is where default parameters shine. Imagine a coffee machine. By default, it might brew black coffee, but it also has options to add milk or sugar. Those are like default parameters. They have a standard value, but you can change them if you want. Def function name, param1, param with default equals default values. Function body, you set a default value by assigning it directly in the parameter list when you define the function, like greeting equals hello. Let's enhance our greet function. Def greet advanced, name greeting equals hello, print greeting name. Now, if we don't provide a greeting when we call greet advanced, it will use hello by default, but we can easily override it. There's a crucial rule with default parameters. They must always come after any non-default positional parameters. Correct. Def func correct, param1, param default equals value, pass. If you put a non-default parameter after a default one, Python won't know which argument corresponds to which parameter, and it will throw a syntax error. Incorrect will cause a syntax error. Def func incorrect, param-default equals value, param1, pass. So always put your optional parameters at the end. Next up, keyword arguments. So far, we've passed arguments by their position. But what if your function has many parameters and remembering their order is a headache? Or what if you only want to pass a value for a specific optional parameter? Keyword arguments let you pass arguments using the parameter's name, like parameter name equals value. This makes your function calls super clear and flexible. Function name, param name 1 equals value 1, param name 2 equals value 2. You can even mix positional and keyword arguments, but there's a rule. All positional arguments must come before any keyword arguments. Correct. Add numbers, 5, num2 equals 3. Incorrect. Add numbers, num2 equals 3, 5. This will cause a syntax error. Keyword arguments are great for readability, especially in functions with many parameters and for easily skipping optional parameters. Let's put this theory into practice. First, let's create a greet function with a default parameter for the greeting. Part 1, default parameters. Def greet with default name greeting equals hello. Greeting name. Now, if I call it with just a name, greet with default Alice, it uses hello by default, but I can easily change it. Greet with default Bob, hi. See how hi overrides the default? Pretty neat. Important rule demo. Remember that rule about default parameters always coming last? Let me show you what happens if we break it. This will cause a syntax error. Def bad function default val equals oops, required val, print required val. If I try to define this, Python immediately throws a syntax error saying non-default argument follows default argument. Always keep those default parameters at the end. Now, let's explore keyword arguments to make our function calls even clearer and more flexible. We'll use our add numbers function from part 1, but this concept applies to any function. Part 2, keyword arguments. Def add numbers, num1, num2, total equals num1 plus num2. Print the sum of num1 and num2 is total. Print calling add numbers with keyword arguments. Add numbers, num1 equals 5, num2 equals 3. Clearer what each number is for. Add numbers, num2 equals 10, num1 equals 20. Order doesn't matter here. Notice how num1 equals 5 and num2 equals 3 explicitly tell Python which value goes to which parameter. This is fantastic for readability. And because we're using keywords, the order doesn't even matter, as you see with num2 equals 10, num1 equals 20. You can even mix them, but remember the rule. Positional arguments first, then keyword arguments. Print calling add numbers with mixed arguments. Add numbers 7, num2 equals 4. Positional first, then keyword. What if I put the keyword argument first? This will cause a syntax error. Add numbers, num2 equals 4, 7. Python throws a syntax error again. Positional argument follows keyword argument, so stick to the rule. Positionals first, then keywords. Now for the fun part. Let's apply everything we've learned to build a simple command line calculator. We'll create functions for add, subtract, multiply, and divide. Here's how we'll structure it. We'll define each operation as its own function, each taking two numbers as parameters. Simple calculator project. Def add, num1, num2, adds two numbers and prints the sum. Result equals num1 plus num2. Print num1 plus num2 equals result. Def subtract, num1, num2, subtracts two numbers and prints the difference. Result equals num1 minus num2. Print num1 minus num2 equals result. Def multiply, num1, num2, multiplies two numbers and prints the product. Result equals num1 times num2. Print num1 times num2 equals result. Def divide, num1, num2, 2. Divides two numbers and prints the quotient. Handles division by 0. If num2 equals 0, print error cannot divide by 0. Else, result equals num1 divided by num2. Print num1 / num2 equals result. Notice those triple quotes? Those are called docstrings. They're a great way to describe what your function does. Good practice. And for divide, we added a little check to prevent division by 0, which would cause an error. Now let's add some code to get input from the user and call our functions. Print basic calculator demo. Get user input for numbers. We'll use a try except block to handle non-numeric input gracefully. Try first num star equals input, enter the first number. Second num star equals input, enter the second number. Convert input strings to floating point numbers. n1 equals float, first num star. n2 equals float, second num star. Call our calculator functions. Add n1, n2. Subtract n1, n2. Multiply n1, n2. Divide n1, n2. Accept value error. Print invalid input. Please enter valid numbers only. Accept exception as E. Print an unexpected error occurred, E. Print calculator demo complete. Here, input gets text from the user. We convert that text to numbers using float so we can perform calculations. And the try except block is super important. It catches potential value error if someone types something that isn't a number. This makes our program more robust. Let's run it. If I entered 10 and 5, you'll see all the operations. Now, what if I enter hello for the first number? See? Invalid input. Please enter valid numbers only. Our error handling worked. This project clearly shows how breaking down a big problem, a calculator, into smaller, manageable functions makes the code easier to write, understand, and debug. Each function does one job, and does it well. All right, time for a challenge to solidify your understanding. Your task is to write a Python function called restaurant greeter. This function should take 3 parameters. 1, customer name, positional. 2, table number, positional. 3 is VIP, with a default value of false. If is VIP is true, the function should print a special VIP greeting like, welcome, customer name. Your VIP table number is ready. Enjoy your exclusive dining experience. Otherwise, if is VIP is false, it should print a standard greeting, welcome, customer name. Your table number is ready. Enjoy your meal. Here are some examples of how you might call your function. Restaurant greeter, Sarah, 7. Restaurant greeter John Doe 12 is VIP equals true. Restaurant greeter table dash number equals 3, customer name equals Alice is VIP equals false. Using keyword arguments. For those who want to explore even further, here are a couple of advanced concepts related to parameters. Arbitrary positional arguments, args. Sometimes you don't know exactly how many positional arguments a function will receive. Args lets you accept any number of positional arguments which get collected into a tuple. Arbitrary keyword arguments. Similarly, arbitrary keyword arguments lets you accept any number of keyword arguments which get collected into a dictionary. These are powerful for very flexible functions. I encourage you to look these up and experiment. It's a great way to deepen your understanding. You made it. Let's quickly recap what we've covered. Functions are your best friends for organizing your code, making it reusable, and keeping it clean. They help you follow the dry, don't repeat yourself principle. Parameters are the inputs you give to your functions, making them flexible. We learned about different types of parameters. Positional parameters are matched by their order. Default parameters provide an optional value if you don't supply one, and they must always come after positional parameters. Keyword arguments let you pass values by name, improving readability and allowing for flexible ordering, as long as all positional arguments come first. You've now mastered passing information into functions. This is a massive step in your Python journey. But what about getting information out of functions? And how do variables behave inside and outside your functions? Ever wonder why some variables in your Python code seem to work everywhere, while others just vanish into thin air? Or how your functions give you back exactly what you need? Today, we're demystifying 2 super important Python concepts. Scope, that's where your variables live, and return values, how your functions communicate results back to you. By the end of this video, you'll be writing much cleaner, more predictable, and powerful Python code. You'll master how functions hand back data, making your program smarter and more efficient. Get ready to level up your Python skills. Let's dive in. All right, let's start with the theory. Understanding these ideas will make your coding journey much smoother. First up, scope. Think of scope as the region or part of your program where a variable can be accessed. It's like the variable's neighborhood. We have local scope. Variables defined inside a function live only within that function. It's like a secret notebook that only you can read. Once the function finishes, those variables are gone. They're private. Def greet. Message equals hello from inside the function. This is a local variable. Print message. Greet. Print message. This would cause an error. Look at this simple example. Message here is a local variable. If I try to print message outside the greet function, Python says, hey, I don't know what message is. It's out of scope. Then we have global scope. Variables defined outside any function are global. Think of it like a public whiteboard that everyone in the office can see and read from. Global-name equals Alice. This is a global variable. Def say hello. Print f hello, global name. Say hello. Print f outside, we still know global name. Here, global name is accessible both inside and outside the say hello function. Pretty handy, right? Now, for the curious, Python actually has a rule for how it looks for variables called the LEGB rule. It stands for local, enclosing function locals, global, and built-in. Don't worry too much about the enclosing part for now, but just know Python searches from the most immediate scope outwards. We're mainly focusing on local versus global today. Next up, return values. What are they? Simply put, when a function does some work, it can send back a result using the return keyword. Imagine your function is a chef. You give the chef ingredients, inputs, and the chef cooks something delicious. The return value is like the dish the chef gives back to you. Without it, the chef just cooks and you get nothing. Def add numbers a, b. Sum result equals a plus b. Return sum result. This sends the result back. Result equals add numbers 5, 3. Print f, the sum is result. In this add numbers function, we calculate sum result. The return sum result line is crucial. It sends 8 back, and we can store it in our result variable. Def no return example. Print, this function prints something. Value equals no return example. Print f, what did the function return value? What happens if a function doesn't explicitly return anything? Python functions always return something. If you don't use return, it implicitly returns none. None is Python's way of saying nothing or empty. See how value here becomes none. Def get greeting name, return hello, name returns a string. Def get numbers list. Return 10, 20, 30, returns a list. Def is positive num, return num greater than 0, returns a boolean true, false. Print get greeting Bob, print get numbers list. Print is positive 7, print is positive -2. You can return all sorts of data types, numbers, strings, lists, dictionaries, booleans, anything. This makes functions incredibly versatile. All right, enough theory. Let's get our hands dirty with some live coding. We'll start by seeing scope in action. Scope scenario 1, modifying global variables and common error. Global variable, global-counter equals 0. Def increment bad. If we try to change global counter directly here, Python thinks we want a new local variable. Global counter equals global counter plus 1. This will cause unbound local error. Print attempting to increment bad global counter. Increment bad. Uncomment to see the unbound local error. Here we have a global variable global counter. Now if I try to directly change global counter inside increment bad like this, and try to run it. Whoa! We get an unbound local error. Python thinks we're trying to create a new local variable called global counter inside the function, but we're also trying to read its value before it's assigned. It's confused. The fix? If you genuinely want to modify a global variable inside a function, you must use the global keyword. Def increment good, global counter, tell Python we mean the global one. Global-counter equals global counter plus 1. Print incremented good, global counter. Print initial global counter, global counter. Increment good. Print after increment good, global counter. Increment good. Print after increment good again, global counter. Like in increment good, this explicitly tells Python, hey, I'm talking about the global counter, not a new local one. Now, when we run increment good, you can see the global counter actually changes. Use global with caution though, as it can sometimes make code harder to follow. Scope scenario 2, accessing local variables outside. Def create local variable. My local var equals I live only in here. Print inside function my local var. Create local variable. Print outside function my local var. This will cause a name error. Next, let's look at accessing a local variable outside its function. We have my local var inside create local variable. If I uncomment this line and try to print it outside, boom, name error. Python says my local var isn't defined. That's because its scope is strictly local to the create local variable function. It's like that secret notebook. You can't read it once the function puts it away. Scope scenario 3, parameters are local variables. Def process data, data item. Data item is a local variable, parameter. Processed item equals data item, upper plus processed. Print inside function processed item, processed item. My data equals hello world. Process data, my data. Print data item. This would also be a name error. Print processed item, this too. Finally, remember that function parameters are also local variables. When my data is passed to processed data, it becomes data item locally within that function. You can't access data item or processed item outside. All right, let's switch gears to return values. This is how functions actually give you something back after they do their work. Return value example 1, returning a number. Def calculate area, length, width, area equals length times width. Return area, send the calculated area back. Call the function and store the result. Room area equals calculate area, 10.5. Print the area of the room is room-area square units. Kitchen area equals calculate area, 7.4. Print the area of the kitchen is kitchen area square units. Here, calculate area takes length and width, calculates the area, and then returns it. See how we can then store that returned value in room area or kitchen area and use it later. This is incredibly powerful. Return value example 2, returning a modified string. Def format name, first last, full name equals last.upper, first.capitalize. Return full name. Formatted equals format name John Doe. Print formatted. Greeting equals format name Jane Smith. Print hello greeting. Functions aren't just for numbers. This format name function takes a first and last name, formats them, and returns the nicely formatted string. Notice how we use string methods like upper and .capitalize, and then return the result. Return value example 3, returning multiple values as a tuple. Def get user info, name equals input, enter your name. Age equals int, input, enter your age. City equals input, enter your city. Return name, age, city, returns a tuple. Get all three values at once. Username, user age, user city equals get user info, unpacking the tuple. Print username, username. Print user age, user age. Print user city, user city. You can also store it as a single tuple. User data tuple equals get user info. Print user data tuple. You can even return multiple values. Python does this by packing them into a tuple. Then you can unpack them directly into separate variables when you call the function, like username, user age, user city equals get user info. Super neat. Common mistake, forgetting to store the returned value. Def calculates sum, AB, total equals A plus B, return total. Print, common mistake. Calculate sum, 10, 20, we called it but didn't save the result. Print, did we see the sum? No, because the returned value was lost. Print, correct way. My sum equals calculate sum 10, 20. Store the returned value. Print, the sum is my sum. Now for a very common mistake. Look at this. We call calculate sum 10, 20, but we don't do anything with the value it returns. The function does calculate 30 and returns it, but if you don't store it in a variable or use it immediately, it's just lost in space. Always remember to capture that return value if you need it later. Fantastic. You've made it this far, so let's test your understanding with a fun challenge. Your challenge is to create the secret message encoder. Task: write a function that takes a word, a string, and an integer shift value as input. Goal: the function should shift each letter in the word by the given shift number. For example, if A is shifted by 1, it becomes B. Return: the function should return the newly encoded word. Hint: look up ORD and char in Python. They convert characters to numbers and vice versa. Think about how to handle letters that wrap around, like Z shifting to A. Pause the video, give it a shot, and come back when you're ready. For those who want to go even deeper, nested functions and closures. Python lets you define functions inside other functions. This introduces more complex scope rules called closures, where inner functions can remember variables from their outer functions. Super cool stuff for later. Docstrings. Get into the habit of using docstrings right after your function definitions. They explain what your function does, its parameters, and what it returns. It's excellent for code readability and professionalism. Now that we know how functions give us back values, what happens when things go wrong? When your program hits unexpected input or situations? Ever had your Python program crash unexpectedly? That dreaded red text in your console? It's frustrating, right? Programs crash because of errors, also called exceptions. When an error hits, your application can break, leaving your users confused and your data potentially messed up. No fun. But what if I told you there's a superhero in Python that can gracefully handle these errors? Meet Try and Accept. They're your powerful mechanism to make your code robust and user-friendly, no matter what unexpected input or situation comes up. By the end of this video, you'll master the try, accept, else, and finally blocks and learn how to write code that doesn't just work, but works reliably. Let's dive in. All right, let's start with the basics. What are errors and exceptions in Python? This will cause a syntax error. Print hello. First, you have syntax errors. These are like grammar mistakes in your code. Python catches them before your program even runs, like forgetting a closing parentheses here. This will cause a zero division error at runtime. Result equals 10 divided by 0. Then we have runtime errors, also called exceptions. These happen while your program is running. For example, trying to divide by 0 or trying to turn text into a number when it's not a number. So why handle them? Well, imagine your user types something wrong. Without error handling, your program just crashes. Game over. With error handling, you can give them a friendly message, let them try again, and keep your application running smoothly. It's all about user experience and program stability. Now, for the core of it, the try except block. Try, code that might cause an error. Print, trying something risky. Except, code to run if an error occurs in the try block. Print, an error happened. The try block is where you put the code that might cause an error. If an error occurs inside try, Python immediately jumps to the except block. If no error happens, the except block is completely skipped. It's like saying, try this, but if it fails, do that instead. Try, num equals int, hello. This causes a value error. Except value error, print, that was not a valid number. Except zero division error, print, you can't divide by zero. You can be specific about which errors you catch. It's usually a good idea to catch specific exceptions like value error or zero division error. This way, you only handle the errors you expect, letting unexpected issues surface for debugging. You can even have multiple except blocks. Try, some risky operation, result equals 10 divided by a. Accept exception as e. Print, f, an unexpected error occurred, e. What if you want to know what the error was? You can capture the error message using accept exception as e. The e variable will hold the details of the exception, which is super helpful for debugging. Try, num equals int, input, enter a number. Accept value error, print invalid input, please enter a number. Else, print f, you entered num, no error occurred. Next up, the else block. This code runs only if no exception occurred in the try block. It's perfect for code that should execute when everything goes smoothly. Try, file equals open, my file txt, r, read file. Accept file not found error, print file not found. Finally, this will always run whether there's an error or not. Print, attempted file operation complete, closing resources. File close. In a real scenario, you'd close the file here. And finally, the finally block. This code always runs no matter what. Whether an exception happened or not, whether it was caught or not, the finally block executes. Think of it for cleanup tasks like closing files or database connections, ensuring resources are released. Here's a full diagram showing how try, except, else, and finally all fit together. It's a powerful flow for robust code. Enough theory. Let's get our hands dirty with some live coding. Open up your favorite Python editor. First, let's see a crash in action, causing a zero division error. Print, starting division, num1 equals 10, num2 equals 0, result equals num1 divided by num2. This line will cause an error. Print f, result, print division complete. If we run this, boom, zero division error. The program stops right there. Now, let's fix it with try except, handling zero division error. Try, result equals num1 divided by num2. Print result. Accept zero division error. Print error, cannot divide by 0. Please provide a non-zero denominator. Print division attempt complete. See? No crash, we get a friendly message and the program continues. Much better. Let's try another common one, value error when converting input. Handling value error for user input. Try, age star equals input, enter your age equals int age star. Print f, you are age years old. Accept value error. Print invalid age, please enter a whole number. If I type ABC here instead of crashing, it tells me invalid age. What if multiple things can go wrong? You can chain except blocks, handling multiple specific exceptions. Try, num star equals input, enter a number. Divisor str equals input, enter a divisor. Num equals int num star. Divisor equals int divisor star. Result equals num divided by divisor. Print result, result. Accept value error. Print error, please enter valid numbers. Accept zero division error. Print error, you cannot divide by 0. Accept exception as E. Catch any other unexpected errors. Print an unexpected error occurred E. See how we handle both specific issues? And that accept exception as E acts as a general fallback for anything else. Now let's bring in else and finally. Using else and finally. Def safe divide A, B, try, result equals A divided by B. Accept zero division error, print division by 0 is not allowed. Return none. Else, print division successful. Return result. Finally, print division attempt finished cleanup phase. Print safe divide 10, 2. Print dash times 20. Print safe divide 10, 0. Print dash times 20. Safe divide 10a. This will still crash if not handled by a general except or specific except for type error. Notice finally always runs, but else only runs when there's no error in the try block. The last case, 10 divided YA, still crashes because we didn't explicitly catch type error there. This highlights why catching exception as E is useful for unknown errors. Let's quickly talk about a few common mistakes. Mistake 1, catching too broadly. Try some code. Result equals 10 divided by 0. Except too broad, this catches everything. Print something went wrong. Using a bare except, this catches every single error, even syntax errors or keyboard interrupts, which can hide real problems. Solution, always try to catch specific exceptions. It gives you more control and clarity. Mistake 2, not user-friendly feedback. Try int oops. Accept value error as E. Print E. This prints the raw Python error. Not giving user-friendly feedback, just printing the raw Python error message isn't helpful for users. Solution, provide clear, simple messages like, please enter a valid number. And a quick one. Mistake number 3, putting too much code in the try block. Only wrap the specific lines that might cause an error. This makes your error handling more precise. Let's put everything together by building a simple command line calculator that's robust against bad input. Robust calculator project. Def calculate, while true, print simple calculator. Print operations, plus, minus, multiply, divide, type quit to exit. Operation equals input, enter operation. If operation.lower equals quit, print exiting calculator, goodbye. Break. If operation not in plus, minus, multiply, divide, print invalid operation. Please choose from plus, minus, multiply, divide. Continue. Go back to the start of the loop. Try num1 str equals input, enter first number, num1 equals float, num1 star, using float for more flexibility. Num2 star equals input, enter second number. Num2 equals float num2 str. If operation equals plus, result equals num1 plus num2. Elif operation equals minus. Equals num1 minus num2. Elif operation equals multiply. Result equals num1 times num2. Elif operation equals divide. If num2 equals 0, raise zero division error, manually raise for consistent handling. Result equals num1 divided by num2. Else, this block is mostly for safety after the initial check. Print an unknown operation error occurred. Continue. Print result num1 operation num2 equals result. Accept value error. Print error invalid number input. Please enter valid numerical values. Accept zero division error. Print error cannot divide by 0. Accept exception as E. Print an unexpected error occurred. E, please try again. Call the calculator. Calculate. See how it gracefully handles non-numbers, division by zero, and even invalid operations? It keeps looping and letting the user correct their mistakes without the program crashing. This is the power of error handling. All right, time for your challenge. Modify our calculator. Can you add error handling for an invalid operation symbol, e.g., if the user types x instead of plus, minus, multiply, or divide before it gets to the numerical input? Think about how you check for valid operations. Hint, you might not even need a try except here, but rather an if statement, which is also a form of input validation. For those eager to learn more, custom exceptions. Look into how to create and raise your own custom exceptions for very specific errors in your application logic. Logging. Instead of just printing errors, explore Python's logging module. It's essential for larger applications to record errors to files or other systems. Context managers with statement. This is a really cool concept, often used with files. It automatically handles setup and cleanup, including error situations. It's a perfect bridge to our next lesson. So, what did we learn today? You've learned that try attempts code, except catches errors, else runs on success, and finally always runs for cleanup. This makes your Python programs resilient and much more user-friendly. Remember, robust code means happier users and more reliable applications. Error handling is a cornerstone of good programming. And speaking of reliability, next up, we'll dive into working with files, read-write. Error handling is absolutely crucial when dealing with files, like if a file isn't found, so your new skills will be put to immediate use. Ever wonder how your favorite apps save your progress or store your data? Like your high scores in a game or those important notes you've saved? Well, it all boils down to file handling. In this video, you'll learn the essential skills of reading from and writing to files in Python. By the end, you'll be able to create, modify, and manage your own data files, a fundamental skill for any Pythonista. So what exactly is a file in programming? Think of a file as a container on your computer's storage, like a document or a spreadsheet, where you can permanently save data. Why is this crucial? Because when your Python script finishes running, any data it was holding in memory just disappears. Files let us store that data so it persists, meaning it stays there even after your program closes. When we work with files in Python, we need to tell Python how we want to interact with that file. Are we reading from it? Writing to it? Both? This is where file modes come in. Let's look at the most common ones. R, read default, opens for reading, error if file doesn't exist. W, write, opens for writing, creates the file if it doesn't exist. Warning, overwrites content if file exists. A, append, opens for writing, creates file if it doesn't exist, adds new content to the end of the file. X, exclusive creation, opens for exclusive creation, failing if the file already exists. T, text mode, default, for text files. B, binary mode, for non-text files like images or executables. The T and B modes are often combined with R, W, or A, so RT is read text mode and WB is write binary mode. Most of the time, we'll be working with text files, so R, W, and A are your main go-tos. To start working with any file, we first need to open it. We do this using Python's built-in open function. It takes at least two arguments, the file path and the mode. File object equals open, filename txt mode. The open function returns a file object, which is what we'll use to actually read from or write to the file. Think of it like a remote control for your file. Now, after you're done with a file, it's super important to close it. If you don't, you can run into issues like data not being saved correctly or the file being locked by your program. Traditionally, you do this with fileObject.close. File equals open, myfile.txt w. File, write, hello. File, close. Don't forget this. But Python offers a much better and safer way, the with statement, also known as a context manager. When you use with, Python automatically takes care of closing the file for you, even if errors occur. With open, myfile.txt w as file, write hello. File is automatically closed here. This is the gold standard for file handling in Python. Always use with. Once a file is open for reading R mode, we have a few ways to get its content. Read. This reads the entire content of the file as a single string. With open, example txt_r as f, content equals f, read. Print content. Read line. This reads just one line from the file. If you call it again, it reads the next line. With open example.txt_r as f, line 1 equals f, read line. Line 2 equals f, read line. Print line 1, line 2. Read lines. This reads all lines from the file and returns them as a list of strings, where each string is one line from the file. With open example txt_r as f, all lines equals f, read lines. Print all lines. To put data into a file, we use write or write lines. Write, this writes a single string to the file. Remember, it doesn't automatically add new lines, so you need to include \n yourself if you want line breaks. With open output.txtw as f write first line of text, f write second line of text. Write lines. This is handy when you have a list of strings and want to write them all to the file. Again, it doesn't add new lines automatically. Lines equals line A, line B, line C. With open output.txtw as f write lines, lines. A crucial point. When you open a file in write mode, if the file already exists, its entire content will be overwritten. If you want to add to an existing file without losing old data, you use append mode. All right, enough theory. Let's jump into some live coding and see all of this in action. Get ready. Okay, let's open up our code editor. We'll start by creating a new Python file. Let's call it file demo py. First, let's see how to create and write to a brand new file using the W mode. Remember, this will create the file if it doesn't exist or overwrite it if it does. Example 1, creating and writing to a new file. Print, example 1, writing to a new file. With open myfirstfile.txtw as file. File write, hello Python file handling. File write, this is a new line of text. Print, content written to myfirstfile.txt. Notice the \n for a new line. Without it, everything would be on one line. Let's run this. Great, now we have our file. Let's try reading its entire content using read. Example 2, reading the entire content of a file. Print, example 2, reading entire file. With open myfirstfile.txtr as file, content equals file, read. Print file content, print content, run it. And there it is, the full text. What if we want to read it line by line? We can loop directly over the file object, which is very efficient. Example 3, reading line by line. Print example 3, reading line by line. With open myfirstfile.txtr as file, line number equals 1. For line in file, print line number, line.strip. Strip removes extra new lines. Line number plus equals 1. The .strip method is useful here to remove any extra new line characters that for line in file might include. Let's run that. Next, let's demonstrate appending to an existing file using the A mode. This won't erase what's already there. Example 4, appending to an existing file. Print, example 4, appending to file. With open myfirstfile.txt as file, write appending a third line now, file, write, and a fourth line, appended. Print content appended to myfirstfile.txt. Let's read it again to confirm. Print confirming appended content. With open myfirstfile.txtr as file, print file read. Let's run this and then confirm by reading the file again. See? The new lines are added at the end. Now, let's talk about some common errors you might run into and how to fix them. The most common one, file not found error. This happens if you try to open a file for reading that doesn't exist, or if you misspell the file name, causing file not found error. Try with open non-existent file.txtr as file, content equals file, read, print content. Except file not found error, print error, the file non-existent file.txt was not found. The solution, double-check your file path and name, or ensure the file exists before trying to read it. If you intend to create it, use W or A mode. Another one, I/O error or unsupported operation. This often happens if you open a file in W, write mode, and then try to read from it without closing and reopening in R mode, causing I/O error/unsupported operation with OpenTempFile.txtW as file. File, write, some text. File, read, this would cause an error. Accept exception as E, print, an error occurred E. Remember, with statements are fantastic because they handle closing the file for you. If you don't use with, forgetting file close can lead to unexpected behavior, like data not being saved or the file being locked by your program. Always use with. Phew, that was a lot of hands-on. You're doing great. Now, let's apply these skills to a real mini project. All right, let's build something practical. We're going to create a simple to-do list manager. This little program will let you add tasks and view existing tasks, all saved to a file so your to-do list persists even after you close the program. First, let's define a function to add a new task. Def add task adds a new task to the do.txt file. With open todo.txt a as file, write task plus \n, print task added. We're using a append mode here so we don't accidentally erase old tasks. Each task gets its own line. Next, a function to view all tasks. Def view tasks reads and displays all tasks from the to-do txt file. Try with open todo.txtr as file, tasks equals file, read lines. If not tasks, print your to-do list is empty. Else, print your to-do list. For I, task and enumerate tasks, print the +1 task.strip, print some dashes, accept file not found error, print no to-do list found yet, add some tasks. Notice the try except file not found error. This makes our program robust so it doesn't crash if to-do. TXT doesn't exist yet. Finally, let's create a simple main menu to interact with our program. Def main function to run the to-do list manager. While true, print to-do list manager, print 1 add task, print 2 view tasks, print 3 exit. Choice equals input, enter your choice 1, 2, 3. If choice equals 1, task equals input, enter the task, add task, elif choice equals 2, view tasks. Elif choice equals 3, print exiting to-do list manager. Goodbye. Break. Else, print invalid choice. Please try again. If name equals main. The if name equals main block just ensures our main function runs when the script is executed directly. Let's run this. Okay, let's try adding a task, learn file handling. Now let's view our tasks. See, it's there. Let's add another, practice Python, and view again. Now let's exit the program, and just to confirm, let's open to-do txt directly. There they are, our tasks are saved. This is a simple example, but it shows the power of file handling for making your programs remember things. All right, time to challenge yourself and reinforce what you've learned. Your mission, should you choose to accept it, is to create a Python script that asks the user for their name and their favorite color, then saves this information to a file called userdata.txt. Here's the catch. If userdata.txt already exists, the new data should be appended, not overwritten. This means you'll need to use the correct file mode. Pause the video, give it a shot, and remember to use what you've learned about file modes. For those who want to go further, here are some ideas for extension activities. Explore handling CSV files, comma-separated values. Many real-world datasets are stored in CSVs, and Python has a built-in CSV module to make working with them much easier. Look into the OS module for more file and directory operations, like checking if a file exists, or even deleting files programmatically. These extensions will make your file handling skills even more powerful. Next up, we'll demystify Python modules and the import statement, learning how to organize your code, reuse functionalities from other files, and tap into Python's vast standard library. This is crucial for writing larger, more manageable programs. You won't want to miss it. Ever wished you could organize your Python code like a pro, reuse awesome functions you've written, and tap into a universe of pre-built tools without having to write them yourself? Today, we're doing just that. We're unlocking your code's superpowers with Python modules and import. By the end of this video, you'll understand what modules are, how to create your own, and how to use the mighty import statement to bring external code into your projects. Get ready to write cleaner, more efficient Python. So what exactly are modules? Simply put, a Python module is just a Py file that contains Python code. This code can be functions, classes, or even just variables. Think of it like this. Imagine you're building with Legos. Each Lego brick has a specific shape and purpose, right? A Python module is like one of these individual Lego bricks. You can build a function in one brick, a variable in another, and then snap them together to build something much bigger and more complex, like a cool spaceship or a castle. What are the big benefits of using modules? First, code organization. Instead of one giant messy file, you can break your code into smaller, manageable pieces. Second, reusability. Write a useful function once, save it in a module, and then use it in any of your projects. And third, it helps avoid naming conflicts. If two different parts of your code use the same variable name, modules help keep them separate. Now let's talk about the import statement. This is your gateway to reusing code. The most basic way to use it is import module name. This brings the whole module into your current script. Import math. Print math.py, output 3, 1415926535897993. Sometimes, module names can be a bit long. That's where import module name as alias comes in handy. You give the module a shorter, more convenient name. Import random as rnd, print rn randint 110, output a random integer between 1 and 10. What if you only need a specific function or variable from a module? You can use from module name import specific item. This avoids bringing in the entire module, keeping your workspace cleaner. From math import pi. Print pi, output 3, 141592535897993. There's also from module name import str. This brings everything from the module directly into your script. While it seems convenient, be cautious. It can lead to naming conflicts if you have functions or variables with the same names in your current script and the imported module. We generally advise against using import str in larger projects. Example of where star can be tricky. In module A pi, my var equals 10. In module B pi, my var equals 20. If you do, from module A import star. From module B import star. Print my var, which my var would it be? It's unpredictable and error prone. Python also comes with many powerful built-in modules. You don't need to install them, they're ready to use. For instance, the math module gives you mathematical functions like square roots and pi. The random module helps you generate random numbers, perfect for games. Import math. Print math sqrt16, output 4.0. Import random. Print random.choice apple, banana, cherry, output a random fruit. All right, enough theory. Let's get our hands dirty and write some code to see this in action. First, let's create our own module. I'm going to open my code editor. I'll create a new file and name it mydoodles.py. Def greet name, return f hello name. Def add ab, return a plus b. Here I've created two simple functions, greet, which takes a name and returns a greeting, and add, which sums two numbers. Crucially, I'm saving this file as my utils. Common mistake alert. If you forget to save your file or save it in a different folder, Python won't be able to find it when you try to import it. Solution: always make sure your module file is saved in the same directory as the script you're trying to import it into, or that its location is added to Python's path. For now, keeping them in the same folder is the easiest way. Now let's create a separate file, say main script py, to import and use our new module, mainscript.py. Import myutils. Print myutils.greet Alice. Result equals myutils. Add 10, 5. Print the sum is result. See how we use myutils.greet and myutils.add? We're calling the functions by first typing the module name, then a dot, then the function name. Let's run this. Perfect. Now let's try importing with an alias. We can make myutils shorter, maybe mu. Main script py, import myutils as mu. Print mu, greet Bob, result equals mu. Add 27. Print the new sum is result. Running this, we get the same great results, but with less typing. What if we only want the greet function and nothing else? We can use selective importing. Main script py, from myutils import greet. From myutils import add, you can import multiple specific items. Print greet Charlie. Print add 82. Notice now we can call greet directly without myutils in front of it. Next, let's quickly see some built-in modules. We'll use math and random. Built-in example pi, import math. Print the value of pi is math pi. Print square root of 64 is math sqrt 64. Import random. Random number equals random. Randinct 1, 100. Print a random number between 1 and 100. Random number. When you run this, Python already knows where to find math and random, and you get instant access to their functions. Troubleshooting tip. You might sometimes see a module not found error. This means Python can't find the module you're trying to import. Most of the time, it's a typo in the module name or the file isn't in the correct directory. Double check your spelling and file location. Great job on the hands-on section. Now let's apply what we've learned to a practical mini project. For our project, we're going to build a simple math helper using modules. Our goal is to create a module named Math Operations that will hold functions for basic math operations. Then we'll create a main calculator that uses these functions. Let's start by creating math operations. Mathoperations.py. Def add xy, return x plus y. Def subtract xy, return x minus y. Def multiply xy, return x times y. Def divide xy. If y equals 0, return error cannot divide by 0. Return x divided by y. Here we have functions for add, subtract, multiply, and divide. I've also added a small check for division by 0 to prevent errors. Now let's create our main calculator script, maincalculator.py. Import math operations. Def run calculator, print welcome to the simple Python calculator. While true, print select operation. Print 1 add. Print 2 subtract. Print 3 multiply. Print 4 divide. Print 5 exit. Choice equals input. Enter choice 1, 2, 3, 4, 5. If choice equals 5, print exiting calculator. Goodbye. Break. If choice in 1, 2, 3, 4, try. Num1 equals float. Input enter first number. Num2 equals float. Input enter second number. Accept value error. Print invalid input. Please enter numbers only. Continue. If choice equals 1, print num1 plus num2 equals math operations. Add num1, num2. Elif choice equals 2, print f num1 minus num2 equals math operations subtract num1, num2. Elif choice equals 3, print f num1 times num2 equals math operations multiply num1, num2. Elif choice equals 4, result equals math operations divide num1, num2. Print f num1 divided by num2 equals result. Else, print invalid input. Please enter a number between 1 and 5. If name equals main, run calculator. In this script, we first import math operations. Then our run calculator function takes user input for numbers and the desired operation. We then call the appropriate function from our math operations module. Notice how clean mainCalculator.py looks because all the actual math logic is neatly tucked away in math operations. Let's run this simple calculator. This demonstrates how logically separating different functionalities into their own modules makes your main script cleaner, easier to understand, and much simpler to manage or update later. You've done great so far. Now, it's time for a coding challenge to solidify your understanding. Your challenge: create a module called conversions that includes functions to convert Celsius to Fahrenheit, kilometers to miles. Then, in a separate script, import and use these functions to perform a conversion based on user input. Hint, remember the formulas. For Celsius to Fahrenheit, it's Celsius times 9 divided by 5 plus 32. For kilometers to miles, it's kilometers times 0, 621371. Ready for more? Let's talk about further exploration. You've learned about built-in modules and creating your own, but there's a vast world of external modules created by other developers. To install these, you use a tool called pip, the Python package installer. Pip lets you get amazing libraries like requests for making web requests or NumPy for powerful numerical operations. We'll cover pip in more detail in future videos, but it's good to know it exists. Finally, for larger projects, you might see something called packages. Packages are simply directories that contain multiple modules, often with a special init py file inside. It's just another way Python helps you organize really big code bases. Let's quickly recap the key takeaways. Modules are .py files for organizing and reusing your code. The import statement is how you bring modules and their contents into your scripts. We saw different import variations like import module as alias, and from module import specific item. And remember, modules make your code cleaner, more modular, and incredibly powerful. Now that you've mastered modules, you're ready to build something awesome. We'll put these skills to the test as we dive into a simple Python project like a number guessing game. You'll be able to build a basic game, understand how programs take your input, make decisions, repeat actions, and even generate random numbers, all in under 10 minutes. Ready? Let's go. Quick reminder, all the code snippets, extra challenges, a quiz, and key takeaways for this lesson are in the description below. Make sure to check them out to practice what you learn. Building this game needs 3 core ideas. First, user input. How do we get your guess? Python's input function. Your name equals input. What's your name? Print hello, your name. Input waits for you to type something and press enter. But remember, it always gives you back text. If you type a number like 25, it's the string 25, not the number 25. To do math, we use int to convert text to a whole number. Age star equals input. Enter your age, e.g. 25. Age int equals int, age star, e.g. 25. Print you will be age int plus 1 next year. If you try int hello, Python gives a value error. We'll handle this. Second, conditional logic. This is how our game tells you too high or too low. We use if, elif, short for else if, and else. Score equals 85. If score is greater than or equals 90, print excellent. Elif score is greater than or equals 70, print good job. Else, keep practicing. Python uses indentation to know which lines belong to which if or elif section. It's super important. Third, loops, specifically the while loop. Our game needs to keep asking for guesses while you haven't guessed the secret number. Counter equals 0. While counter is less than 3, print counting counter. Counter plus equals 1. This increases counter by 1. Print done counting. The loop runs as long as counter is less than 3. If we forget counter plus equals 1, it's an infinite loop. It'll run forever. We also use break to stop a loop immediately, like when you guess correctly. All right, let's code. Open your editor. First, we need the computer to pick a random secret number. Python has the random module for this. We import random at the top. Then random, randint1 100 gives us a whole number between 1 and 100. Import random, print, welcome to the number guessing game. Secret number equals random, randint1 100. Print, I'm thinking of a number between 1 and 100. Now for the main game loop. We'll use a while loop that continues until our guess matches the secret number. We'll also track the number of guesses. Guess equals 0. Start with a guess that doesn't match. Guess count equals 0. While guess not equals secret number, try. Guess star equals input, enter your guess. Guess equals int, guess star. Guess count plus equals 1, increase count for each valid guess. Accept value error. Print, oops, that's not a whole number, try again. Continue, skip to the next loop cycle if input is bad. See that try except? It's crucial. If the user types ABC, int would crash our program. Accept value error catches it, prints our error message, and continue makes the loop ask for input again without crashing. Inside our loop, after a valid guess, we tell the user if their guess is too high or too low. If guess is less than secret number. Too low, try again. If guess is greater than secret number, print too high, try again. Else, print congratulations, you guessed secret number in guess count guesses. Break, we guessed it. Exit the loop. When guess equals secret number, the else block runs, prints our win message, and break stops the while loop because the game is over. Let's play a round. I'll guess 50. Too low. Okay, 75. Congratulations, you guessed 75 in 2 guesses. Great, it's working. And that's it. A full playable number guessing game. Now for a challenge to really test your new skills. Limited guesses. Modify the game so the player only gets a certain number of tries, e.g. 7 guesses. If they run out, tell them the secret number and end the game. Play again. Can you wrap the whole game in another while loop so the user can choose to play multiple rounds without restarting the program? Hint. Ask input. Play again at the end and use lower. These challenges will help you combine everything we've learned in new ways. You just built your very first interactive Python game. You now understand how to get user input with input and convert it to numbers with int. How to make your program make decisions using if, elif, and else. How to repeat actions with while loops and stop them with break. How to handle errors like value error using try except, and how to generate random numbers for endless fun. This is a huge step in your Python journey. In our next lesson, we'll explore how AI tools can actually help you write code faster and smarter, and we'll dive into some more advanced Python topics. Ever wondered how to supercharge your Python coding? What if you could write better code, faster, and even explore cutting-edge concepts like never before? Coding is always changing, right? To stay ahead, we need to leverage new tools and dive into more advanced topics. We'll talk about how AI can be your coding co-pilot and then briefly explore exciting advanced Python topics that will take your skills to the next level. Get ready to transform your coding journey. So what exactly are AI coding tools? Simply put, they are AI programs trained on huge amounts of code. They learn patterns and help you write your own code. Let's look at some of the most popular and great AI tools shaping how we code today. GitHub Copilot, your AI pair programmer. It suggests lines of code and even whole functions as you type, directly in your editor. Tab9, another excellent AI code completion tool that uses machine learning to provide highly relevant code suggestions. Amazon Code Whisperer offers real-time code recommendations and can even scan for security vulnerabilities. Cursor, an AI-first code editor designed from the ground up to integrate AI capabilities directly into your coding workflow, offering chat and intelligent edits. Deep Code, Snipe Code, focuses on analyzing code for bugs, quality issues, and security vulnerabilities. ChatGPT and Google Gemini. While general-purpose AI, they are incredibly powerful for explaining code, debugging, generating snippets from natural language, and brainstorming coding solutions. These tools broadly help in several ways. Code completion generation. They predict what you want to type and complete lines or even whole functions for you. Code refactoring, optimization. They can analyze your code for inefficiencies and suggest improvements, helping you write cleaner, more efficient code. Bug detection, debugging assistance. They can spot potential problems in your code even before you run it, saving you a lot of headaches. Natural language to code. Imagine telling the AI, write a Python function to read a file, and it just does it. These tools can turn your plain English instructions into actual code snippets. So what are the big benefits? They make you more productive, help reduce errors, and even help you learn new coding patterns by seeing how the AI solves problems. But, and this is important, AI is a tool, not a replacement for you. Don't just blindly accept what it generates. It can sometimes give you incorrect code or code that's not the best solution. Also, there are questions about where the code comes from. Is it unique? Is there any risk of copying? Always understand the code the AI gives you and test it thoroughly. It's your responsibility. Now, you might be eager to see these AI tools in action, right? How do you actually get them working in your own editor? How do you prompt them to generate code or find bugs? Well, great news. We have a comprehensive series coming soon that will dive deep into exactly how to use these AI tools in your coding workflow. We'll show you step by step how to set them up, how to write effective prompts, and how to use them for everything from generating simple functions to refactoring complex projects. This video is just the appetizer. In that dedicated series, we'll cover common mistakes, best practices, and real-world scenarios in detail. We'll teach you this golden rule. Don't blindly accept code. Always read through it, understand every line, and make sure it fits your needs. And how to use AI for boilerplate code, the repetitive stuff, but meticulously review complex logic that's unique to your problem. Plus, we'll emphasize how to test AI-generated code rigorously, treating it just like any other code you write to catch any hidden issues. Okay, let's step it up. We'll now briefly touch upon the realm of advanced Python topics. These are crucial for building more efficient, robust, and scalable applications. Think of it this way. Basic Python gives you the tools to build a house. Advanced Python teaches you how to design a skyscraper, manage complex plumbing, or build a smart home system. It's about optimizing, scaling, and handling more intricate challenges. These topics include concepts that allow your programs to handle many operations at once without slowing down, write cleaner and more reusable code, or even build powerful frameworks and libraries. Just like with AI tools, mastering these advanced concepts requires dedicated learning. So get ready for another exciting announcement. All right, your turn. Here's a challenge to get you thinking about AI tools and their potential. I'd love to hear your thoughts. And speaking of next steps, our Python journey doesn't stop here. The world of advanced Python is vast and exciting. So what's your next step? Subscribe to our channel and hit that notification bell because we have 2 special surprises for you. Thanks for watching and happy coding.